Hello there, and welcome. Tonight I want to take you somewhere special, somewhere quiet and profound, far from the gentle glow of your bedside lamp, far from the familiar walls of your room. We're going to journey together into the vast darkness between worlds, to meet a visitor that came calling not so long ago, a visitor whose presence raised questions we're still trying to answer. It's a question that might seem unlikely at first, perhaps even far-fetched, but stay with me, because what if a comet, drifting silently through the darkness millions of miles away, could reach out and touch the very satellites that orbit our world? What if something so ancient, so distant, could whisper to our most modern machines? Picture yourself floating above the Earth right now, looking down at our beautiful blue marble suspended in the infinite black. Below you, the planet turns slowly. City lights twinkling like scattered diamonds across the continents, and all around you, invisible to the naked eye, hundreds of satellites drift in their precise orbits, each one a testament to human ingenuity, each one listening, watching, measuring. These silent sentinels of our technological age maintain their vigil day and night, connecting our phone calls, guiding our navigation systems, monitoring our weather, watching over us in ways we rarely stop to consider. They float there in the darkness, these extensions of ourselves, these mechanical ambassadors we've sent to live between Earth and space. Now, as you float there in this peaceful void, turn your gaze outward, away from Earth's warm glow, out into the deeper darkness where the stars shine with their ancient light. Somewhere out there, beyond the orbit of Mars, beyond the asteroid belt, beyond even the great gas giants, there are travelers moving through the darkness. These are the comets, the wanderers of our solar system, following paths that take them on journeys lasting thousands, sometimes millions of years. They are messengers from the earliest days of our solar system, carrying within their frozen hearts the very materials from which our worlds were born. In the early months of 2019, astronomers working with the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected something moving in the darkness. It was faint at first, just a smudge of light against the star field, barely distinguishable from the countless other points of light that fill our telescopes. But this one was moving, following a path that would bring it closer to our sun, closer to us. They designated it C2019Y4, though we would come to know it simply as Comet Atlas. At first, it seemed like it would be just another comet, one of dozens that sweep through the inner solar system each year, most passing unnoticed by all but the most dedicated observers. But Atlas was different. As it drew closer to the sun through late 2019 and into 2020, something remarkable began to happen. The comet began to brighten, not gradually as most comets do, but dramatically, exponentially. Astronomers around the world turned their instruments toward this unexpected celestial show. Some began to wonder if we might be witnessing the approach of the next great comet, one that would light up our skies the way Hale-Bopp did in 1997, or Hyakutake in 1996. The excitement in the astronomical community was palpable, a gentle stirring of anticipation for what might unfold. Consider for a moment the journey this comet had taken to reach us. Atlas began its life billions of years ago, in the outer reaches of our solar system, in a region we call the Oort cloud. This is a sphere of icy bodies that surrounds our solar system like a vast frozen shell, extending perhaps a light year or more from the sun. Out there, in that eternal cold and darkness, countless chunks of ice and rock drift in slow, patient orbits, undisturbed for eons. They are the leftover building blocks of our solar system, the materials that never quite made it into planets, preserved in deep freeze since the dawn of our cosmic neighborhood. Something, perhaps the gentle gravitational tug of a passing star, or the accumulated effect of countless tiny perturbations over millions of years, nudged Atlas from its distant orbit and sent it falling toward the sun. This journey would have taken thousands of years, a slow, silent fall through the darkness. For most of that time, the comet would have been invisible, too far from the sun to reflect much light, too cold to show any activity. It was a ghost drifting through the void, carrying its cargo of primordial ice and dust toward a distant appointment with our star. As Atlas crossed the orbit of Neptune, then Uranus, then Saturn, the sun's influence began to grow stronger. The comet was still frozen solid, but deep within its nucleus subtle changes were beginning. The increasing warmth of sunlight, still faint at these distances but growing stronger with each passing year, was starting to penetrate the comet's surface. By the time it crossed the orbit of Jupiter, the transformation had begun in earnest. The ices that had been frozen for billions of years were beginning to sublimate, turning directly from solid to gas, creating a thin atmosphere around the comet's nucleus. This is the magic of comets, this awakening that happens as they approach the sun. What was once a dark, silent chunk of ice and rock becomes something ethereal, something beautiful. The gases escaping from the nucleus carry with them tiny particles of dust, creating the comet's coma, that glowing cloud that surrounds the nucleus. And as the solar wind, that constant stream of charged particles flowing from the sun, encounters this coma, it pushes the gas and dust away from the comet, creating those magnificent tails that have captivated humanity since we first looked up at the night sky. Atlas developed a particularly impressive tail as it approached the inner solar system. By March of 2020, the comet's coma had grown to be hundreds of thousands of kilometers across, larger than Jupiter, though of course incomparably less dense, more like a whisper of matter spread across an enormous volume of space. The tail stretched even farther, millions of kilometers long, a gossamer thread of dust and ions pointing away from the sun. To observers on Earth using telescopes, Atlas appeared as a fuzzy green glow, the color coming from diatomic carbon molecules in the coma fluorescing in the sunlight. But here's where our story takes an interesting turn, a twist that transforms Atlas from simply another comet, passing through our neighborhood into something more mysterious, more intriguing. As the comet made its closest approach to Earth in May of 2020, passing about 116 million kilometers from our planet, something else was happening, something that wouldn't become apparent until much later, when scientists began looking through the data from that period. Some of our satellites, those precise instruments orbiting Earth, recorded anomalies during the comet's passage. They were subtle, barely noticeable, the kind of tiny deviations that might easily be dismissed as noise or normal variations. But they were there, recorded in the data, waiting to be discovered. Now, you might be wondering how a comet, passing at such an enormous distance, more than 3/4 of the distance from Earth to the Sun, could possibly affect satellites orbiting just a few hundred or 1,000 kilometers above our planet. It seems impossible, doesn't it? The gulf of space between them is so vast, the comet itself so insubstantial despite its impressive appearance. And yet, we live in a universe of subtle connections, where influences can travel across seemingly impossible distances, where the gentle pressure of sunlight can push spacecraft off course, where the gravitational pull of distant planets can shape the orbits of asteroids. The satellites that recorded these anomalies were not dramatic failures or obvious malfunctions. They were more like whispers in the data, slight variations in signal strength, minor fluctuations in orientation sensors, small discrepancies in timing systems. The kind of things that satellite operators see from time to time and usually attribute to space weather, the normal variations in the electromagnetic environment around Earth caused by solar activity. But the timing was curious, coinciding with Atlas's passage, and the pattern was intriguing, affecting multiple satellites in subtle but similar ways. To understand how this might be possible, we need to think about space not as empty void, but as a medium filled with fields and particles, currents and waves. The space between Earth and the comet might seem empty to our eyes, but it's actually filled with a solar wind, with magnetic fields, with streams of charged particles, with electromagnetic radiation across the entire spectrum. It's a dynamic, ever-changing environment, and both Earth and the comet exist within it, both influencing it and being influenced by it. Comets, you see, are not just chunks of ice and rock. As they approach the sun and begin to sublimate, they become electromagnetically active. The interaction between the solar wind and the comet's coma creates a complex electromagnetic environment around the comet. The comet develops what scientists call an induced magnetosphere, a region where the comet's own materials interact with the solar magnetic field to create local magnetic structures. These structures can be surprisingly extensive, reaching out far beyond the visible coma. The tail of a comet is not just a passive stream of dust and gas blown away by the solar wind. It's an active, dynamic structure with its own electromagnetic properties. The ion tail, in particular, is made up of charged particles, ions that have been stripped of electrons by solar radiation. These ions interact with the solar wind in complex ways, creating waves and instabilities that propagate along the tail. The tail becomes, in effect, a giant electromagnetic antenna, millions of kilometers long, interacting with the solar wind and potentially generating signals that could propagate through space. Now, imagine our satellites, orbiting Earth in their precise paths, their sensitive instruments constantly monitoring their environment, maintaining their orientation, receiving and transmitting signals. These satellites are designed to operate in the near-Earth space environment, shielded to some degree by Earth's magnetosphere but still exposed to the variations of space weather. They're equipped with sensors that can detect the slightest changes in magnetic fields, the tiniest variations in charged particle flux, the most subtle shifts in the electromagnetic spectrum. As Atlas passed by, even at its great distance, it's possible that the comet's electromagnetic influence extended much farther than we might expect. Perhaps the comet's tail, that enormous structure of charged particles and dust, created disturbances in the solar wind that propagated inward toward Earth. Perhaps the comet's induced magnetosphere interacted with the solar wind in ways that generated waves or instabilities that traveled along magnetic field lines, eventually reaching Earth's magnetosphere and affecting the environment where our satellites operate. This is not as far-fetched as it might sound. We know that disturbances in the solar wind can affect satellites. Solar flares and coronal mass ejections regularly cause problems for satellite operations, creating what we call geomagnetic storms that can disrupt communications, affect GPS accuracy, and even damage satellite electronics. If the Sun, at 150 million kilometers away, can affect our satellites, why not a comet passing at a similar distance, especially one as active as Atlas? The data from that period is tantalizing but not conclusive. Satellite operators reported various minor anomalies, brief communication dropouts that corrected themselves, small errors in GPS positioning that required recalibration, unexpected variations in solar panel output, minor glitches in attitude control systems. None of these were serious enough to cause concern at the time, and most were attributed to normal space weather variations. It was only later, when researchers began looking for correlations with the comet's passage, that the pattern began to emerge. But Atlas had another surprise in store for us, one that would add another layer to this mystery. As the comet approached the Sun, astronomers watching it noticed something troubling. The comet's brightness, which had been increasing so dramatically, suddenly began to fluctuate. Images showed that the nucleus appeared elongated, then fragmented. Atlas was breaking apart. This cosmic visitor that had travelled so far, that had survived for billions of years in the outer darkness, was disintegrating as it approached the Sun. This fragmentation was not violent or explosive. It was more like a gentle dissolution, the comet's nucleus quietly coming apart into smaller and smaller pieces. By April 2020, what had been a single nucleus had become a cloud of fragments, each one continuing along essentially the same orbit but slowly spreading out, creating an extended cloud of material where once there had been a single, solid body. The comet that had promised to be a spectacular sight in our skies was fading, dissolving back into the cosmic dust from which it had formed so long ago. This fragmentation changed everything about Atlas's interaction with the inner solar system. Instead of a single nucleus with its coma and tail, we now had dozens, perhaps hundreds of smaller fragments, each producing its own small coma, each contributing to an extended, diffuse cloud of gas and dust. The comet's influence was no longer concentrated, but spread out over a much larger volume of space. The tail became more complex, more turbulent, as material from multiple fragments interacted with the solar wind. Think about what this means for our satellite mystery. If a single comet could potentially influence satellites at Earth, what about a dispersed cloud of fragments? The electromagnetic effects might be different, perhaps weaker in some ways, but more widespread, creating a broader zone of influence. The interaction with the solar wind would be more complex, potentially generating a wider range of electromagnetic phenomena. The fragmentation of Atlas might have transformed it from a single source of disturbance into a distributed field of subtle influences. As we contemplate this possibility, it's worth remembering that we're still in the early days of understanding how objects in our solar system interact electromagnetically. For most of human history, we've thought of celestial mechanics purely in terms of gravity, of objects pulling on each other with invisible threads of gravitational force. But as we've sent more instruments into space, as we've developed more sensitive detectors, we've discovered that the electromagnetic interaction between celestial bodies is just as real, just as important, though often more subtle. The Earth itself is an electromagnetic object, with its magnetic field extending far out into space, creating our magnetosphere that protects us from the worst of the solar wind. The Sun is obviously electromagnetically active, its magnetic field extending throughout the solar system, carried by the solar wind. Even the other planets have their electromagnetic signatures, from Jupiter's enormous magnetosphere to Mars's remnant magnetic fields preserved in its rocks. And now we're beginning to understand that comets, too, are electromagnetic actors in this cosmic drama. The investigation into whether Atlas actually affected our satellites is ongoing. Scientists are combing through archives of satellite data from the period of the comet's passage, looking for patterns, correlations, anomalies that might have been overlooked at the time. They're developing computer models to simulate how a fragmenting comet might interact with the solar wind, and whether those interactions could propagate to Earth. They're comparing the Atlas passage with other comet encounters, looking for similar patterns that might confirm or refute the hypothesis. This is how science works, slowly, carefully, building understanding piece by piece. We may never know for certain whether Atlas interfered with our satellites. The effects, if they existed, were so subtle, the system so complex, that definitive proof may be impossible to obtain. But the question itself is valuable, pushing us to think about our cosmic environment in new ways, to consider connections we might not have imagined before. As you lie there tonight, perhaps you can imagine those satellites still circling overhead, maintaining their silent watch. And perhaps you can imagine too the fragments of Atlas, still out there somewhere, continuing their journey around the Sun, slowly dispersing, gradually returning to the cosmic dust from which they came. The comet and the satellites never came close to each other in any conventional sense, separated by a gulf of space that our minds can barely comprehend. And yet, they may have touched each other in ways we're only beginning to understand, connected by invisible threads of electromagnetic influence that span the vast emptiness between worlds. This is the universe we inhabit, a place where nothing exists in true isolation, where every object influences every other object in ways both obvious and subtle. The gravity of distant galaxies shapes the light from even more distant quasars. The solar wind from our Sun pushes against the interstellar medium, creating a bubble around our solar system, and perhaps, just perhaps, a dying comet's last breath can whisper to our satellites, a gentle reminder that we're all part of one interconnected cosmic system. The story of Atlas raises profound questions about our relationship with the cosmos. We tend to think of space as something out there, separate from our daily lives, relevant only to astronomers and astronauts. But if a comet can potentially affect our satellites, those crucial links in our global communication network, then space is not separate from us at all. We exist within it, dependent on it, vulnerable to its variations and surprises. Every time you use GPS to navigate, every time you check the weather forecast, every time you make an international phone call, you're relying on satellites that float in that supposedly empty space, subject to influences we're still discovering. Consider the delicate balance required to keep a satellite functioning properly. These machines must maintain precise orientations, keeping their solar panels pointed at the sun for power, their antennas pointed at Earth for communication, their instruments pointed at whatever they're designed to observe. They must compensate for the constant pressure of sunlight, the variations in Earth's magnetic field, the occasional impact of micrometeoroids. They operate in an environment of extreme temperature variations, bombarded by radiation, isolated from any possibility of physical maintenance. Now add to this already challenging environment the potential influence of a passing comet. Even the tiniest additional disturbance could require compensation, could drain battery reserves, could introduce errors into sensitive measurements. The satellites are designed with margins of safety, redundant systems, error correction protocols. But they're optimized for the known challenges of their environment. The influence of a fragmenting comet millions of kilometers away was probably not something their designers explicitly considered. This brings us to an interesting thought about our technological civilization. We've built these incredible networks of satellites, these orbital infrastructures that our modern world depends on. But we've built them based on our current understanding of the space environment, an understanding that continues to evolve. Every new discovery about how objects interact in space, every unexpected influence we uncover, adds to our knowledge, but also reveals how much we still don't know. The Atlas event, whether it actually affected satellites or not, serves as a gentle reminder of our place in the cosmic order. We are not separate from the universe. We are part of it, subject to its rhythms and surprises. Our technology, no matter how advanced, operates within the natural world, not apart from it. And that natural world extends far beyond Earth's atmosphere, encompassing the entire solar system and beyond. As we drift deeper into contemplation of this cosmic mystery, it's worth pausing to appreciate the sheer scale of what we're discussing. When we talk about Atlas passing 116 million kilometers from Earth, that number is so large it becomes almost meaningless. Let's try to put it in perspective. If you could drive a car at highway speed continuously without stopping, it would take you over 130 years to cover that distance. If you could travel at the speed of a commercial jetliner, it would still take over 13 years. Light itself, the fastest thing in the universe, takes over 6 minutes to cross that gulf. And yet, across that enormous distance, there might have been an interaction, a connection, a whisper of influence from comet to satellite. This is the magic and mystery of our universe, where distance doesn't always mean isolation, where influences can propagate across seemingly impossible gulfs of space and time. The electromagnetic force, one of the 4 fundamental forces of nature, has infinite range. In principle, every charge particle in the universe influences every other charge particle, though the influence weakens with distance. But it never quite reaches zero, never completely disconnects. This interconnectedness extends beyond just electromagnetic forces. Gravity too has infinite range. The Earth's gravity influences Atlas, even at its great distance, just as Atlas's gravity, minuscule though it may be, influences Earth. These influences are too small to measure, too small to matter in any practical sense, but they exist nonetheless. We're all connected in this cosmic web of forces, all influencing each other in ways large and small, obvious and subtle. The fragmentation of Atlas adds another dimension to this story. When we think of a comet breaking apart, we might imagine some violent event, some sudden catastrophe. But the reality was much gentler, more gradual. The comet simply couldn't hold itself together against the stresses of its journey. The heat from the sun created pressure from sublimating gases. The gravity of the sun and planets pulled differently on different parts of the nucleus. Internal stresses that had been frozen in place for billions of years were suddenly released. The result was not an explosion but a slow dissolution, like watching an ice sculpture melt in slow motion, except instead of melting, the comet was sublimating, turning directly from solid to gas, and the pieces were drifting apart in the vacuum of space. Each fragment continued to follow essentially the same orbit, but small differences in velocity, tiny variations in the forces acting on each piece, caused them to slowly spread out, creating an extended cloud where once there had been a single object. This cloud of fragments would have created a much more complex electromagnetic environment than a single comet. Each fragment, no matter how small, would contribute its own gases to the overall coma. The interaction with the solar wind would happen not at a single point, but across an extended region. The tail would be fed by multiple sources, creating a more turbulent, more complex structure. If there were electromagnetic effects from this interaction, they would be distributed, perhaps creating a broader but weaker influence, or perhaps creating multiple points of stronger interaction. We can imagine the solar wind encountering this cloud of fragments like a river flowing around not a single boulder, but a field of rocks. The flow would be disrupted in complex ways, creating eddies and currents, waves and turbulence. In the electromagnetic realm, this could translate to a variety of phenomena: waves propagating along magnetic field lines, instabilities in the plasma of the solar wind, variations in the density and velocity of charged particles. These disturbances wouldn't stay localized around the comet. The solar wind is constantly flowing outward from the sun, carrying magnetic fields and disturbances with it. Any disruption created by the comet would be carried along by this flow, potentially reaching Earth's magnetosphere days or weeks later. By then, the connection to the comet might not be obvious. The disturbance would have evolved, interacted with other features in the solar wind, been modified by the ambient conditions of interplanetary space. This is one of the challenges in determining whether Atlas actually affected our satellites. The space environment is so complex with so many sources of variation that isolating the influence of a single event is extremely difficult. The sun is constantly varying in its output, sending out flares and coronal mass ejections. Other planets create their own disturbances in the solar wind. Cosmic rays from outside the solar system provide another source of energetic particles. Against this background of constant variation, detecting the subtle signature of a comet's influence is like trying to hear a whisper in a noisy room. But scientists are patient, and they have powerful tools at their disposal. By analyzing data from multiple satellites, they can look for patterns that might not be apparent in any single data set. By comparing the timing of anomalies with the comet's position and activity, they can search for correlations. By modeling the interaction between the comet and the solar wind, they can predict what kinds of effects might be expected and then look for those specific signatures in the data. This detective work is ongoing, and it may take years before we have a clearer picture of whether Atlas truly influenced our satellites. But even if the answer turns out to be no, even if the anomalies were just coincidence, the investigation itself is valuable. It pushes us to think more carefully about how objects in our solar system interact, about the subtle connections that exist across vast distances, about the ways our technology might be vulnerable to cosmic influences we haven't fully considered. As we continue to expand our presence in space, with more satellites, space stations, and eventually settlements on other worlds, understanding these subtle interactions becomes increasingly important. We need to know what kinds of influences our equipment might experience, what kinds of protections we need to build in, what kinds of events we need to monitor and predict. The Atlas event, whether it had real effects or not, is a learning opportunity. a chance to refine our understanding and improve our preparations. There's something poetic about the idea that a comet, one of the most ancient types of objects in our solar system, might interfere with satellites, some of our most modern technological achievements. It's a meeting of old and new, of natural and artificial, of the pristine materials from the birth of our solar system and the sophisticated products of human intelligence. The comet carries information from billions of years ago. Frozen in its ice and dust, the satellites carry information from today in their electronic signals and data streams, and perhaps, for a brief moment, these two information carriers interacted, the ancient touching the modern across the gulf of space. We turn our attention now from the cosmic visitor to the silent sentinels that may have felt its touch, these remarkable machines we've placed in orbit around our world. As you settle deeper into comfort, imagine ascending through Earth's atmosphere, rising through the layers of air that grow thinner and thinner until you emerge into the vast quietude of space. Here, in this realm between Earth and the cosmos, hundreds of satellites maintain their eternal vigil, circling our planet in precise, predetermined paths. They are our eyes and ears in space, our extended senses, and during the passage of Comet Atlas, some of them recorded whispers of something unusual, something that shouldn't have been there. To understand what these satellites might have experienced, we need to first appreciate what they are and how exquisitely sensitive they've become. Each satellite is essentially a collection of the most precise instruments we can build, wrapped in protective shells and powered by wings of solar panels that drink in sunlight. They're designed to detect the faintest signals, to measure the smallest variations, to maintain positions accurate to centimeters while traveling at speeds of several kilometers per second. They are in many ways more sensitive than our own senses, able to perceive things we cannot see, hear frequencies we cannot detect, feel magnetic fields we cannot sense. Consider the GPS satellites, perhaps the most familiar of our orbital infrastructure. There are currently about 30 of them operational, circling Earth at an altitude of roughly 20,000 kilometers, each one carrying atomic clocks so precise they can measure time to within billionths of a second. These clocks must be this accurate because GPS works by timing how long it takes signals to travel from the satellites to receivers on Earth. Since those signals travel at the speed of light, an error of just 1 billionth of a second translates to a position error of about 30 centimeters. The entire system is a marvel of precision, a dance of synchronized timekeepers circling our planet. During the period when Atlas was making its closest approach to Earth, several GPS satellites reported tiny discrepancies in their timing, not enough to significantly affect navigation for most users, but enough to be noticed by the monitoring systems that constantly check the health and accuracy of the constellation. The atomic clocks themselves didn't malfunction, but there were subtle variations in the signals as they propagated through space, as if something in the space environment had changed ever so slightly, affecting the speed or path of the radio waves. These variations were on the order of nanoseconds, billionths of a second, barely perceptible even to our most sensitive instruments. In the normal operation of the GPS system, such variations are expected and corrected for. The signals must pass through Earth's ionosphere, a layer of charged particles in our upper atmosphere that can slow and bend radio waves. Solar activity can change the density of the ionosphere, causing variations in signal propagation. Ground stations constantly monitor these effects and broadcast corrections. But the variations during the Atlas passage seemed different, not quite matching the usual patterns of ionospheric disturbance. Then there were the communication satellites, those vital links in our global information network. These satellites, orbiting at various altitudes from a few hundred to tens of thousands of kilometers, relay signals between ground stations, enabling everything from international phone calls to internet connectivity in remote areas. They operate across a wide range of frequencies, from radio waves to microwaves, each frequency carefully chosen to balance factors like atmospheric absorption, available bandwidth, and regulatory requirements. Several communication satellite operators reported brief signal degradations during the Atlas passage period. Nothing dramatic, nothing that interrupted service, but noticeable in the quality metrics that are constantly monitored. It was as if there was additional noise in the signal, a faint static that shouldn't have been there. The effect was most pronounced on certain frequencies, particularly those in the higher ranges of the radio spectrum, suggesting that whatever was causing the interference had frequency-dependent properties. The Earth observation satellites told their own subtle story. These are the satellites that monitor our planet's weather, track changes in vegetation, measure sea levels, and observe countless other aspects of Earth systems. They carry incredibly sensitive instruments, radiometers that can detect tiny variations in thermal radiation, spectrometers that can identify specific molecules in the atmosphere, radar systems that can measure surface heights to millimeter accuracy. Some of these satellites recorded anomalous readings during the Atlas period. Not in their observations of Earth, but in their calibration data, the reference measurements they use to ensure their instruments are working correctly. Many Earth observation satellites carry calibration targets, reference sources with known properties that they periodically observe to check their sensitivity and accuracy. During the comet's passage, some of these calibration measurements showed tiny deviations, as if there was an additional source of radiation or interference that wasn't accounted for in the normal calibration procedures. The pattern was particularly interesting in satellites that measure magnetic fields. Earth has a fleet of satellites dedicated to monitoring our planet's magnetosphere, that invisible shield that protects us from the solar wind and cosmic radiation. These satellites carry magnetometers capable of detecting variations in magnetic field strength of less than 1 nanotesla, about 1/50,000th of Earth's surface magnetic field. They orbit at various altitudes, some skimming the top of our atmosphere, others venturing out into the magnetosphere's outer reaches. During the Atlas passage, several of these magnetometer-equipped satellites detected what appeared to be waves in the magnetic field, oscillations that didn't match the usual patterns of geomagnetic activity. The waves were extremely weak, barely above the noise level of the instruments, but they appeared to have a coherent structure, a regular pattern that suggested they were real phenomena rather than random noise. The frequency of these waves was in the range of a few millihertz, meaning each oscillation took several minutes to complete, far too slow for human senses to detect, but well within the capability of patient or precise satellite instruments. What makes these magnetic field observations particularly intriguing is their timing and distribution. The waves didn't appear simultaneously at all satellites, but seemed to propagate through the magnetosphere, appearing first at satellites on the sunward side of Earth, and later at those in Earth's magnetic tail. This propagation pattern suggests that something was disturbing the solar wind upstream of Earth, creating waves that then interacted with our magnetosphere. The satellites in geostationary orbit, hovering 36,000 kilometers above Earth's equator, provided another piece of the puzzle. These satellites maintain fixed positions relative to Earth's surface, making them ideal for continuous monitoring of weather systems or for providing consistent communication coverage to specific regions. Because they stay in one place relative to Earth, any variations in their environment are easier to detect than for satellites in lower, faster orbits. Several geostationary satellites reported unusual variations in their solar panel output during the Atlas period. Solar panels convert sunlight to electricity, and their output is normally very predictable, varying only with the angle of sunlight and the gradual degradation of the panels over time. But during the comet's passage, some satellites recorded fluctuations in power output that didn't correlate with any changes in solar illumination. It was as if something was intermittently absorbing or scattering a tiny fraction of the sunlight before it reached the panels. The effect was minuscule, a variation of less than 1% in power output, but it was detected by multiple satellites and showed a temporal pattern that seemed to correlate with the comet's position relative to Earth and the Sun. The fluctuations were most pronounced when the comet was positioned such that material from its tail might be passing between the Sun and Earth, even though that material would be spread so thin as to be completely invisible to the naked eye. Perhaps most mysteriously, several satellites reported issues with their star trackers during this period. Star trackers are instruments that satellites use for navigation and orientation. They work by taking pictures of the star field and comparing them to an internal star catalogue, allowing the satellite to determine precisely which direction it's pointing. They're incredibly reliable, as the stars provide a fixed reference frame that doesn't change over human timescales. But during the Atlas passage, some star trackers reported difficulty in identifying stars, as if there was a faint haze or additional light source confusing their algorithms. The effect was subtle enough that backup orientation systems could compensate, but it was unusual enough to be logged as an anomaly. When engineers later analysed the star tracker images, they found what appeared to be a very faint, diffuse glow in some frames, not bright enough to be seen by eye, but enough to slightly wash out the faintest stars that the trackers use for precision orientation. This ghostly glow didn't appear to be coming from any particular direction, but seemed to be a general increase in the background light level. It's worth noting that comets can produce diffuse glows through a process called fluorescence, where molecules in the coma absorb solar radiation and re-emit it at different wavelengths. If material from Atlas's tail had spread through the inner solar system, even at extremely low densities, it might have created a faint fluorescent glow that sensitive star trackers could detect. The cumulative picture from all these satellites is one of subtle but pervasive disturbance, as if the space environment around Earth had been gently stirred by the comet's passage. No single anomaly was dramatic enough to cause concern, and indeed many went unnoticed until researchers specifically went looking for correlations with the comet's position and activity. But taken together, they suggest that something unusual was happening in near-Earth space during that period. To appreciate how remarkable it would be for a comet to affect satellites at such distances, we need to understand just how empty space really is, or perhaps more accurately, how empty it seems to be. The space between Earth and where Atlas passed contains fewer particles per cubic meter than the best vacuum we can create in laboratories on Earth. If you could somehow collect all the matter in a column of space stretching from Earth to the comet's closest approach distance, with a cross-section of 1 square meter, you would have less material than in a single grain of sand. And yet, this seemingly empty space is filled with fields and forces, with photons and particles, with waves and currents that we're only beginning to fully understand. The solar wind streams through it at hundreds of kilometers per second. Carrying magnetic fields and charged particles, cosmic rays zip through at nearly the speed of light. Radio waves from natural and artificial sources propagate in all directions. It's a complex, dynamic environment, and our satellites sit right in the middle of it, their sensitive instruments recording every variation, every fluctuation, every whisper of activity. The satellites themselves contribute to this environment. Each one is surrounded by its own small sphere of influence, its electronics generating electromagnetic fields, its surfaces charging up from interaction with the space environment, its thrusters occasionally firing to maintain position. They're not passive observers, but active participants in the electromagnetic ecosystem of near-Earth space. This makes detecting external influences even more challenging, as any anomaly must be distinguished from the satellite's own electromagnetic signature. The charging of satellite surfaces is particularly interesting in the context of the Atlas mystery. In space, satellites can accumulate electrical charge through various mechanisms. They're bombarded by charged particles from the solar wind and Earth's radiation belts. They emit electrons through photoelectric effect when sunlight hits their surfaces. Different parts of the satellite can charge to different voltages, creating potential differences that can lead to electrical discharges, like tiny lightning bolts jumping between components. During the Atlas passage, several satellites reported unusual charging events, not dangerous levels, as satellites are designed to handle significant charging, but patterns that didn't match the typical charging environment. It was as if the flux of charged particles around the satellites had changed, either in intensity or in energy distribution. Some satellites reported more negative charging than usual, suggesting an increase in electron flux. Others reported more positive charging, suggesting either a decrease in electrons or an increase in positive ions. These charging anomalies might provide a clue to the mechanism by which Atlas could have influenced satellites. If the comet's tail, even at its enormous distance, changed the distribution of charged particles in the solar wind, those changes could propagate to Earth's magnetosphere and affect the charging environment around satellites. It's a subtle effect, but satellite charging is one of the most sensitive indicators of changes in the space environment. The temperature variations reported by some satellites add another layer to the mystery. Satellites must carefully manage their temperature, using radiators to dissipate heat generated by their electronics and heaters to keep components warm during eclipse periods when they pass through Earth's shadow. The thermal environment of a satellite is normally very predictable, depending mainly on solar illumination and the satellite's orientation. But during the Atlas period, some satellites reported small, unexpected temperature variations. Components that should have been at steady-state temperatures showed tiny fluctuations. Radiators seemed slightly less efficient than normal. Heater duty cycles changed marginally. The effects were small enough to be within design margins, but they suggested that something in the thermal environment had changed. One possibility is that dust from the comet's tail, even at extremely low concentrations, might have affected the radiative properties of space around the satellites. Dust particles, even microscopic ones, can absorb and re-emit infrared radiation, potentially creating a very slight greenhouse effect in the immediate vicinity of the satellites. Or perhaps the dust particles, if they were charged, might have been attracted to or repelled by the satellite's own electrical charges, creating a very thin cloud of material around each satellite that affected its thermal properties. The data storage systems on several satellites also reported anomalies during this period. Modern satellites store vast amounts of data in solid-state memory systems, and these systems can be affected by energetic particles that flip bits from 0 to 1 or vice versa. This is a known phenomenon in space, and satellites use error-correcting codes to detect and fix these single-event upsets. But during the Atlas passage, the rate of bit flips seemed to increase slightly on some satellites, suggesting a change in the radiation environment. This is particularly interesting because comets can be sources of energetic particles. As the solar wind interacts with the comet's coma, it can accelerate ions to high energies. These particles might not be energetic enough to be considered cosmic rays, but they could still be capable of causing single-event upsets in sensitive electronics. If Atlas was producing such particles, and if they were somehow reaching Earth's vicinity, they could explain the increased bit flip rate. The attitude control systems of satellites provided yet another set of clues. These systems keep satellites pointed in the right direction, using a combination of sensors to determine orientation and actuators like reaction wheels or thrusters to make adjustments. They're constantly making tiny corrections to compensate for various torques acting on the satellite: atmospheric drag for low-orbit satellites, solar radiation pressure, gravity gradient effects, and magnetic torques from interaction with Earth's magnetic field. During the Atlas passage, several satellites reported that their attitude control systems were working slightly harder than usual, making more frequent corrections, using more fuel or wheel momentum than predicted. The differences were small, within normal operational variations, but when analysed statistically across multiple satellites, a pattern emerged. It was as if there was an additional very small force acting on the satellites, requiring compensation by the attitude control systems. What could cause such a force? One possibility is that the comet's tail, even at its extreme thinness, might have exerted a tiny pressure on the satellites. We know that solar radiation exerts pressure on satellites, enough that it must be accounted for in orbit predictions. Could dust or gas from the comet's tail have exerted a similar, though much smaller pressure? The calculations suggest the effect would be almost impossibly small, but when dealing with instruments capable of detecting accelerations of millionths of a meter per second squared, even the smallest effects become detectable. Another intriguing observation came from satellites equipped with particle detectors. These instruments are designed to measure the flux and energy of charged particles in space, contributing to our understanding of space weather and radiation hazards. During the Atlas passage, some of these detectors recorded what appeared to be a new population of particles, with energies and trajectories that didn't match the usual sources. The solar wind, cosmic rays, or particles trapped in Earth's radiation belts. These anomalous particles appear to come in bursts, lasting minutes to hours, with no clear correlation to solar activity or geomagnetic conditions. Their energy spectrum was unusual, peaked at energies higher than typical solar wind particles, but lower than cosmic rays. Their composition, as far as could be determined from the limited data, suggested they might be water group ions, the kind that would be expected from a comet's sublimating ice. The trajectory analysis was particularly puzzling. The particles didn't seem to be coming directly from the direction of the comet, which would be expected if they were simply material from the tail reaching Earth. Instead, they appeared to be coming from various directions, as if they had been scattered or deflected by some mechanism. One possibility is that particles from the comet were being caught and accelerated by magnetic field structures in the solar wind, creating a diffuse cloud of energetic particles that eventually reached Earth. The communication delays experienced by some satellites add yet another dimension to the mystery. These weren't delays in the satellites themselves, but in the propagation of signals between satellites and ground stations. Radio signals traveling at the speed of light normally take a very predictable time to travel from a satellite to Earth, but during the Atlas passage, some signals seemed to take slightly longer than they should have, as if they were being slowed or taking a longer path. The delays were tiny, measured in nanoseconds, but they were detected by the precise timing systems used for satellite communication and navigation. The effect was frequency-dependent, with higher frequencies showing greater delays, suggesting that whatever was causing the delay was dispersive, affecting different wavelengths differently. This is characteristic of propagation through a plasma, an ionized gas, raising the possibility that material from the comet had somehow increased the plasma density along the signal path. To truly understand whether Atlas could have whispered to our satellites across the vast gulf of space, we must journey now to the very heart of what a comet is, travelling back through billions of years to witness the birth of these cosmic wanderers. Close your eyes and imagine yourself drifting backward through time, past the age of dinosaurs, past the formation of Earth itself, back to when our solar system was nothing more than a vast cloud of gas and dust, slowly rotating in the darkness between the stars. This is where our story truly begins, in that primordial nebula that would eventually give birth to our sun, our planets, and the comets that still visit us today. 4.5 billion years ago, there was no Earth beneath us, no sun to warm us, only an enormous cloud of material, perhaps light years across, composed mostly of hydrogen and helium left over from the Big Bang, but seasoned with heavier elements forged in the hearts of earlier generations of stars. This cloud was cold, so cold that even molecules of water, methane, and ammonia were frozen into tiny grains of ice, mixed with microscopic particles of rock and dust. It was from this mixture of ice and dust that comets would eventually form, preserving within their frozen hearts a sample of the raw materials from which our entire solar system was built. Something disturbed this cloud, perhaps the shock wave from a nearby supernova, perhaps gravitational interactions with passing stars, and it began to collapse. As it collapsed, it spun faster, like a figure skater pulling in their arms, and the cloud flattened into a disk. At the center, where the density and pressure were highest, the material grew hot enough to ignite nuclear fusion, and our sun was born. But farther out in the disk, where temperatures remained cold, the ice and dust began to stick together, growing from microscopic grains to pebbles, from pebbles to boulders, from boulders to the building blocks of planets and comets. In the inner solar system, where the young sun's heat was strong, the ice sublimated away, leaving only rock and metal to form the terrestrial planets like Earth and Mars. But beyond what we now call the frost line, roughly where Jupiter orbits today, it remained cold enough for ice to survive. Here, the giant planets formed, their massive gravity sweeping up vast amounts of gas and ice. And here too, countless smaller bodies formed, icy planetesimals that would become the comets we see today. But not all of these icy bodies stayed where they formed. The gravitational influence of the giant planets, particularly Jupiter and Neptune, scattered many of them to the far reaches of the solar system. Some were flung out entirely, becoming interstellar wanderers. Others were sent into vast elongated orbits that took them far from the sun but kept them gravitationally bound to our solar system. Over millions of years, these scattered icy bodies formed what we now call the Oort cloud, a vast spherical shell of comets surrounding our solar system at distances of thousands to perhaps 100,000 times the Earth-Sun distance. The Oort cloud is a place of profound cold and darkness. The sun, so brilliant and warm here at Earth's distance, appears as merely the brightest star among many from the Oort cloud. Temperatures hover just a few degrees above absolute zero. Time seems to slow down in this frozen realm, where comets drift in orbits so vast that a single journey around the sun can take millions of years. It's a cosmic deep freeze, preserving these ancient chunks of ice and dust essentially unchanged since the birth of our solar system. Atlas spent most of its existence in this frozen wilderness, a dark, silent sentinel drifting through the void. For billions of years it experienced almost nothing, no warmth, no light beyond starlight, no change except the slow, patient wheel of its orbit around the distant sun. The ice within it remained frozen harder than any rock on Earth, compressed by its own gravity into forms of ice that don't exist naturally on our warm planet. Mixed within this ice were grains of rock and dust, organic molecules formed in the interstellar medium, perhaps even microscopic diamonds formed in the death throes of ancient stars. The nucleus of Atlas, like all comet nuclei, was not a solid ball of ice, but rather a loosely bound collection of smaller pieces, held together by weak gravity and frozen into place by the cold. Scientists often describe comets as dirty snowballs or icy dirt balls, but the reality is more complex and fascinating. Imagine a cosmic rubble pile made of chunks ranging from dust grains to boulders, all frozen together with various ices, not just water ice, but frozen carbon dioxide, carbon monoxide, methane, ammonia, and dozens of other compounds that exist as gases in Earth's environment, but are solid at the temperatures of deep space. This structure makes comets incredibly fragile by planetary standards. The gravity holding them together is so weak that you could easily jump off a small comet and never come back. The material strength is low, more like a loosely packed snowball than solid ice. There are voids and caverns within the nucleus, spaces where the material never quite came together during the comet's formation. It's a porous, heterogeneous structure, different in every comet and even different in different parts of the same comet. When something disturbed Atlas's orbit and sent it falling toward the inner solar system, this ancient, fragile structure began its transformation. As the comet crossed the orbit of Neptune, still far from the sun's warmth, the first subtle changes began. The temperature rose from near absolute zero to merely extremely cold. Cosmic rays, which had been slowly altering the surface chemistry for billions of years, now had less time to work as the comet picked up speed in its fall toward the sun. By the time Atlas crossed the orbit of Jupiter, the transformation was beginning in earnest. The sun's radiation, though still weak at this distance, was strong enough to begin sublimating the most volatile ices. Carbon monoxide and methane, frozen solid in the Oort cloud, began to turn directly from solid to gas, creating the first wisps of what would become the comet's coma. These gases, escaping from the nucleus, carried with them tiny particles of dust that had been frozen in place for billions of years. This is one of the most remarkable aspects of comets. They don't melt like ice on Earth. In the vacuum of space, there's no air pressure to allow liquid water to exist. Instead, the ice sublimates, turning directly from solid to gas, like dry ice does on Earth. This sublimation doesn't happen uniformly across the comet's surface, but is concentrated in areas where the ice is exposed or where the surface is darker and absorbs more sunlight. These active regions become jets, fountains of gas and dust erupting from the nucleus. As Atlas continued its approach to the Sun, more and more ice began to sublimate. Water ice, the main component of most comets, begins to sublimate significantly around the orbit of Mars. The escaping water vapor, along with other gases, formed an atmosphere around the nucleus called the coma. This coma can be enormous, sometimes larger than Jupiter, though it's so thin that it would be considered a hard vacuum by Earth standards. The density of gas in a comet's coma is lower than the best vacuum chambers we can create in laboratories. Within this coma, remarkable chemistry takes place. The Sun's ultraviolet radiation breaks apart molecules, creating a soup of ions, radicals, and neutral species. Water molecules are broken into hydrogen and hydroxyl radicals. Carbon compounds are transformed into various species that can fluoresce in sunlight, giving comets their characteristic greenish glow. Dust particles released from the nucleus are heated by sunlight and begin to emit infrared radiation. It's a dynamic, ever-changing environment, a natural laboratory for chemical processes that can't easily be replicated on Earth. The dust released from the nucleus tells its own story. These particles range from microscopic grains smaller than smoke particles to pebbles and even larger chunks. They're made of silicates, like many rocks on Earth, but also contain organic compounds, complex molecules containing carbon, hydrogen, oxygen, and nitrogen. Some of these organics are prebiotics, the building blocks of life, formed in the cold of space and preserved in the comet's ice for billions of years. When we see a comet's dust tail, we're seeing these ancient particles being released into space, some of which will eventually fall to Earth as meteor showers. The interaction between the comet and the solar wind creates the comet's most spectacular features, its tails. Actually, most comets have two distinct tails. The dust tail is made of particles pushed away from the Sun by radiation pressure, the gentle but persistent push of sunlight itself. This tail curves slightly, following the comet's orbit, because the dust particles continue to orbit the Sun even as they're pushed outward. The ion tail, on the other hand, is made of charged particles. Ions created when solar ultraviolet radiation strips electrons from molecules in the coma. These ions are caught by the solar wind's magnetic field and dragged directly away from the Sun, creating a straight tail that can stretch for millions of kilometers. The ion tail is particularly interesting from an electromagnetic perspective. It's essentially a stream of plasma, a gas of charged particles interacting with the solar wind's magnetic field. This interaction creates a variety of electromagnetic phenomena. Waves propagate along the tail. Instabilities develop where the solar wind meets the cometary plasma. Magnetic field lines are draped around the comet, creating an induced magnetosphere, a region where the comet's own material affects the local magnetic environment. This electromagnetic activity isn't just passive. Comets can generate their own magnetic fields through a process called charge separation. As dust and gas escape from the nucleus, they can become electrically charged through various mechanisms. Photoionization by solar ultraviolet light creates positive ions. Electron impact ionization from solar wind electrons creates more ions. The photoelectric effect, where sunlight knocks electrons off dust grains, leaves the grains positively charged. These charged particles, moving in the solar wind's magnetic field, generate electric currents, and these currents create their own magnetic fields. The scale of these electromagnetic phenomena is staggering. While the comet's nucleus might be only a few kilometers across, its coma can be hundreds of thousands of kilometers in diameter, and its tails can stretch for millions of kilometers. The ion tail in particular can be thought of as a giant electromagnetic antenna, potentially generating and transmitting low-frequency radio waves as plasma instabilities develop and propagate along its length. These waves, though weak, travel at the speed of light and could, in principle, be detected at great distances. Atlas developed a particularly impressive tail system as it approached the Sun. Observations showed that its ion tail extended at least 5 million kilometers, and possibly much farther. The dust tail was broader but shorter, spreading out in a fan as particles of different sizes were pushed away from the Sun at different rates. Both tails were dynamic, changing from day to day as the comet's activity varied, and as it encountered different conditions in the solar wind. The composition of Atlas, as determined from spectroscopic observations, was fairly typical for a long-period comet from the Oort cloud. Water was the dominant volatile, making up perhaps 80% of the escaping gas. Carbon monoxide was also abundant, particularly important because it can sublimate at greater distances from the Sun than water, driving activity when the comet is still far from the Sun. Other detected species included carbon dioxide, methane, ammonia, and various organic compounds including formaldehyde and methanol. But Atlas had peculiarities too. The ratio of different isotopes, variants of elements with different numbers of neutrons, provided clues about where and when the comet formed. The deuterium to hydrogen ratio in the water suggested that Atlas formed in the outer regions of the early solar system, where temperatures were cold enough for deuterium-rich water to condense. The presence of certain organic molecules suggested that some of the comet's material might have formed in interstellar space before the solar system even existed. The dust from Atlas was equally revealing. Analysis of the light scattered by the dust showed that it contained silicates, minerals similar to those found in asteroids and terrestrial rocks. But there were also more exotic materials, crystalline silicates, that must have been heated at some point in their history, perhaps in the inner solar system before being incorporated into the comet. There were organic-rich particles, dark and rich in carbon, possibly including complex molecules that could be precursors to biological compounds. The size distribution of the dust was interesting too. Most of the mass was in larger particles, millimeter-sized or bigger, but most of the number was in tiny grains, smaller than the wavelength of visible light. These tiny particles are particularly important for electromagnetic effects because they can become highly charged and are easily influenced by electromagnetic forces. They're also efficient at scattering and absorbing certain wavelengths of light, potentially affecting the optical properties of space in the comet's vicinity. As Atlas approached its perihelion, its closest approach to the Sun, the stresses on its fragile nucleus increased dramatically. The heating was uneven, with the sunward side receiving much more energy than the night side. This created thermal stresses as different parts of the nucleus expanded and contracted at different rates. The sublimation of ices created pressure from within, as gas tried to escape through the overlying layers of dust and less volatile material. The rotation of the nucleus, which may have been chaotic rather than smooth, added mechanical stresses as different parts of the comet experienced different centrifugal forces. These stresses were ultimately too much for Atlas's weak structure to bear. The fragmentation likely began with cracks developing in the nucleus, perhaps along pre-existing boundaries between the constituent chunks that had been frozen together billions of years ago. As these cracks widened, gas could escape more easily, accelerating the sublimation and further weakening the structure. Eventually, pieces began to separate, each one becoming a mini-comet with its own coma and tail. The fragmentation of Atlas wasn't a single event, but a process that continued over weeks. First, the nucleus split into a few large pieces. Then these pieces fragmented further. By the time the comet reached its closest approach to the Sun, what had been a single nucleus, perhaps 2 kilometers across, had become a cloud of fragments, the largest no more than a few hundred meters across, accompanied by countless smaller pieces down to dust grain size. This fragmentation fundamentally changed how Atlas interacted with the solar wind. Instead of a single point source of gas and dust, there was now an extended cloud of sources. Each fragment contributed its own stream of material to the overall coma and tail. The electromagnetic environment became more complex, with multiple regions of charge separation, multiple sources of plasma, multiple sites where waves and instabilities could develop. The total surface area exposed to sunlight increased dramatically with fragmentation, potentially increasing the overall rate of sublimation. More surface area meant more sites for gas to escape, more regions where dust could be released, more places where electromagnetic phenomena could originate. It's possible that the fragmentation actually increased Atlas's potential to influence the electromagnetic environment of the inner solar system, even as it spelled doom for the comet itself. Understanding the anatomy of a comet like Atlas helps us appreciate just how complex these objects are. They're not simple dirty snowballs, but intricate dynamic systems with physical, chemical, and electromagnetic processes operating across a huge range of scales. From the microscopic chemistry happening on dust grain surfaces to the million-kilometer-long ion tail interacting with the solar wind, comets are natural laboratories for studying matter and energy under extreme conditions. The electromagnetic nature of comets becomes even more fascinating when we consider the specific properties of their tails, those ethereal appendages that have captured human imagination since ancient times. As you drift deeper into relaxation, imagine yourself floating alongside Atlas as it approached the Sun, watching as its magnificent tail began to unfold like a cosmic flower, blooming in slow motion. This tail, stretching millions of kilometers through space, was not merely a beautiful spectacle, but a dynamic electromagnetic system, a whispering veil of charged particles and dust that might have been capable of influences we're only beginning to understand. The tail of a comet is born from violence, though it appears peaceful to our eyes. As the sun's radiation strikes the comet's nucleus, it doesn't gently warm the ice, but rather rips molecules apart with ultraviolet photons, tears electrons from atoms, and creates a turbulent flow of material escaping into space. Each molecule of water that sublimates from the nucleus begins a journey that will transform it completely. First, it escapes as a neutral molecule, moving at speeds of hundreds of meters per second. Then, within hours or days, solar ultraviolet radiation breaks it apart, splitting water into hydrogen and hydroxyl radicals. Further interactions with sunlight and solar wind particles ionize these fragments, stripping away electrons and creating charged particles that respond to electromagnetic forces. This transformation from neutral gas to ionized plasma is crucial for understanding how a comet's tail might influence distant satellites. Neutral gas, no matter how much of it there might be, has limited electromagnetic effects. But plasma, that fourth state of matter consisting of charged particles, is electromagnetically active. It conducts electricity, responds to magnetic fields, generates waves, and can transmit disturbances across vast distances. When we look at a comet's ion tail, we're seeing a river of plasma flowing through space, a conductor that connects different regions of the solar system in ways that neutral matter cannot. The ion tail of Atlas was particularly impressive and perhaps particularly influential. Observation showed that it was highly structured, not a smooth stream but a complex system of filaments, knots, and waves. These structures weren't static but evolved continuously, driven by variations in the solar wind and changes in the comet's own activity. Sometimes the tail would appear to disconnect and reform, a phenomenon that occurs when the solar wind's magnetic field reverses polarity. Other times, bright knots of material would travel along the tail, like waves propagating along a cosmic string. These structures in the ion tail are manifestations of plasma physics processes that scientists are still working to fully understand. When the solar wind, itself a plasma flowing from the sun at hundreds of kilometers per second, encounters the plasma generated by the comet, the interaction is complex and non-linear. It's not like wind-blowing smoke, where the smoke simply flows with the wind. Instead, the two plasmas interact electromagnetically, generating instabilities, accelerating particles, and creating waves that can propagate both upstream and downstream from the interaction region. One of the most important processes in the ion tail is called mass loading. As the solar wind flows past the comet, it picks up ions created from the comet's atmosphere. These cometary ions are initially slow-moving, but they're accelerated by the solar wind's electromagnetic fields to match its speed. This acceleration doesn't happen instantly, but over a distance called the pickup length. During this acceleration, the ions gyrate around magnetic field lines, creating waves and instabilities that propagate through the plasma. The mass loading process is particularly interesting because it can extend far beyond the visible tail. Cometary ions, once accelerated to solar wind speeds, continue to travel outward through the solar system. They remain distinguishable from solar wind ions by their composition and energy distribution, at least for a while. Spacecraft have detected cometary ions millions of kilometers from the comet itself, far beyond the visible tail. If Atlas was producing a significant number of ions, they could have been carried by the solar wind throughout the inner solar system, potentially reaching Earth's magnetosphere. The dust tail tells a different but equally fascinating story. Unlike the ion tail, which is shaped by electromagnetic forces, the dust tail is shaped primarily by radiation pressure, the gentle push of sunlight itself. Each dust particle released from the nucleus becomes a tiny spacecraft, its trajectory determined by the balance between the sun's gravity, pulling it inward, and sunlight pushing it outward. Smaller particles feel more radiation pressure relative to their mass, so they're pushed more strongly away from the sun. Larger particles are less affected and tend to follow orbits closer to the comet's own path. But even the dust tail has electromagnetic properties that might be relevant to our satellite mystery. Dust particles in space don't remain electrically neutral. They're bombarded by solar ultraviolet radiation, which can knock electrons off their surfaces through the photoelectric effect. They're also hit by electrons and ions from the solar wind, which can either add or remove charge. The result is that most dust particles in a comet's tail carry an electrical charge, typically positive but sometimes negative depending on their size and composition. These charged dust particles respond to electromagnetic forces in addition to gravity and radiation pressure. They can be accelerated or decelerated by electric fields, deflected by magnetic fields, and can contribute to the overall charge density of space in the comet's vicinity. When billions upon billions of charged dust particles are present, they create a dusty plasma, a mixture of regular plasma and charged dust that has unique properties, different from either pure plasma or neutral dust. The charging of dust particles in Atlas's tail would have depended on many factors: the size of the particles, their composition, their distance from the sun, and the local plasma environment. Smaller particles tend to charge more strongly relative to their mass, making them more susceptible to electromagnetic forces. Particles rich in certain materials, particularly those that easily emit electrons when hit by ultraviolet light, charge differently than others. The charging can also be variable, with particles gaining and losing charge as they encounter different conditions. As Atlas fragmented, its tail became even more complex. Instead of material streaming from a single source, there were now multiple sources, each fragment contributing its own stream of gas and dust. These streams didn't simply merge smoothly, but interacted with each other, creating turbulence and structure in the tail. The fragmentation may have also released different types of material, as interior ices that had been shielded from solar radiation were suddenly exposed. The electromagnetic effects of this fragmented tail could have been quite different from those of an intact comet. The multiple sources might have created multiple regions of wave generation, potentially producing a broader spectrum of electromagnetic emissions. The increased surface area from fragmentation likely increased the total production rate of ions and charged dust, potentially enhancing the tail's electromagnetic activity. The spatial distribution of sources might have created interference patterns, regions where waves from different sources reinforced or cancelled each other. Consider the scale of what we're discussing. Atlas's tail at its peak extended at least 5 million kilometers, possibly much more. That's more than 13 times the distance from Earth to the Moon. If you could somehow travel along the tail at the speed of a commercial airliner, it would take you more than 7 months to traverse its length. Throughout this enormous volume, electromagnetic processes were occurring. Ions were being created and accelerated, dust was being charged, waves were propagating, and magnetic fields were being twisted and stretched. The tail wasn't a static structure, but a dynamic flow. Material was constantly being added at the comet end and flowing away at the other end. The travel time for ions along the tail was typically days to weeks, while dust particles moved more slowly, taking weeks to months to traverse the tail's length. This meant that the tail at any given moment contained material released from the comet over an extended period, a record of the comet's recent activity frozen in space. The interaction between Atlas's tail and the solar wind would have created a variety of wave phenomena. When the solar wind encounters an obstacle like a comet, it generates bow waves, similar to the waves that form in front of a boat moving through water. These waves can steepen into shocks, regions where the plasma properties change abruptly. Behind the shock, in the comet's wake, turbulence develops, creating a spectrum of waves at different frequencies and wavelengths. Some of these waves are in the ultra-low frequency range, with periods of minutes to hours. These waves can travel along magnetic field lines like vibrations along a string. Potentially propagating far from their source, they can accelerate particles, heat plasma, and trigger instabilities. If such waves were generated by Atlas and propagated along solar wind magnetic field lines that connected to Earth's magnetosphere, they might have been detected by our satellites as the magnetic field oscillations that were observed. The possibility of electromagnetic emissions from the tail is particularly intriguing. When charged particles are accelerated, they emit electromagnetic radiation. In the comet's tail, particles are constantly being accelerated by electric fields, by magnetic forces, by wave-particle interactions. Most of this radiation is at very low frequencies, far below what we normally think of as radio waves. But low-frequency radio emissions from comets have been detected by spacecraft, confirming that comets are indeed radio sources. Could these emissions from Atlas have reached Earth and affected our satellites? The power of such emissions is typically very low, and they spread out as they propagate through space, becoming weaker with distance. But satellites are equipped with extremely sensitive receivers, designed to detect faint signals from deep space. If Atlas was producing radio emissions, even weak ones, and if they happened to be at frequencies that satellites were sensitive to, they might have been detected as increased noise or interference. The charged dust in Atlas's tail presents another mechanism for potential satellite influence. As the Earth-Moon system moved through space, it's possible that we encountered streams of charged dust particles that had been released from the comet days or weeks earlier. These particles, though individually tiny, collectively carry charge and momentum. If a satellite encountered such a stream, the impacts could have affected its surface charging, created small amounts of plasma around the spacecraft, or even generated electromagnetic pulses as charged particles struck the satellite's surface. The density of such dust streams would be extremely low, perhaps only a few particles per cubic kilometer. But satellites present a large cross-section, and over time, even rare impacts can have cumulative effects. Moreover, the electromagnetic effects of charged particle impacts can be disproportionate to their mechanical effects. A single charged dust grain hitting a satellite at high speed can create a small plasma cloud that briefly changes the electromagnetic environment around the spacecraft. The fragmentation of Atlas may have enhanced these dust-related effects. When a comet fragments, it releases not just the dust that would normally sublimate from the surface, but also dust that had been trapped in the interior. This can include different types of particles, possibly with different charging properties. The fragmentation can also create a broader distribution of particle sizes, from large chunks down to microscopic grains, each population with its own dynamics and electromagnetic properties. As we contemplate these possibilities, it's important to remember that space is not empty, but filled with a complex web of electromagnetic fields and particle populations. The solar wind carries the sun's magnetic field throughout the solar system, creating a structure called the heliospheric current sheet, a vast spiral of electric current that extends from the sun to the outer planets. Comets moving through this environment are like boats moving through a river, creating wakes and disturbances that propagate both upstream and downstream. Atlas's trajectory brought it relatively close to Earth in cosmic terms, though still at an enormous distance by human standards. At its closest approach, the comet was about 116 million kilometers from Earth, but its tail, extending millions of kilometers in the anti-sunward direction, created a much larger zone of influence. Depending on the geometry of the encounter, Earth might have passed through the extended tail structure, or at least through regions of space that had been modified by the comet's passage. The timing of Atlas's visit was also interesting from an electromagnetic perspective. The comet reached its peak activity during a period of relatively quiet solar activity, near the minimum of the solar cycle. During solar minimum, the solar wind is typically more stable and uniform, which might have allowed the comet's influence to propagate more coherently through the inner solar system. During solar maximum, with its frequent flares and coronal mass ejections, any cometary effects might have been overwhelmed by solar variability. The polarization of a light from Atlas's tail provided additional clues about the electromagnetic environment. Light scattered by dust particles becomes polarized, and the degree and orientation of polarization depends on the particle's properties and the scattering geometry. Observations showed that the polarization varied across the tail and changed over time, suggesting variations in dust properties or charging states. Highly charged dust particles can affect the polarization of scattered light, potentially providing a remote sensing method for detecting electromagnetic activity in the tail. The spectroscopic observations of Atlas revealed emission lines that are signatures of specific ions and molecules. Some of these emissions are prompt, occurring immediately when molecules are excited by solar radiation. Others are delayed, occurring when excited states decay after some time. The intensity and profile of these emission lines can provide information about the density, temperature, and velocity of material in the tail, as well as the electromagnetic processes occurring there. One particularly interesting aspect of Atlas's tail was its color. The ion tail appeared blue-green, characteristic of carbon compounds like C2 and CN fluorescing in sunlight. The dust tail appeared more yellowish, the color of sunlight reflected from dust particles. But careful observations revealed subtle color variations within each tail, suggesting variations in composition or physical processes. These color variations might indicate regions of different electromagnetic activity, places where particle acceleration or wave generation was particularly strong. The interaction between the two tails, ion and dust, is another source of electromagnetic complexity. The ion tail, being controlled by electromagnetic forces, can move independently of the dust tail. When the solar wind magnetic field changes direction, the ion tail can be disconnected and reformed, while the dust tail continues largely unaffected. But the two tails are not completely independent. Charged dust particles feel electromagnetic forces and can be influenced by the electric and magnetic fields associated with the ion tail. Conversely, the presence of charged dust can affect the propagation of waves and the acceleration of ions. As Atlas approached the Sun and its activity increased, the boundary between the comet and the solar wind became more complex. This boundary, called the cometopause, is where the pressure from the comet's expanding atmosphere balances the pressure from the solar wind. Inside the cometopause, cometary material dominates. Outside, the solar wind dominates. But the boundary is not sharp or static. It fluctuates with variations in the comet's activity and the solar wind conditions, creating a dynamic interaction region where electromagnetic processes are particularly intense. The cometopause of Atlas would have been a site of strong electromagnetic activity. Here, the solar wind is slowed and deflected around the comet, creating electric currents that flow along the boundary. These currents generate magnetic fields that can be much stronger than the ambient solar wind field. Waves are generated as the solar wind becomes unstable at the boundary. Particles are accelerated as they cross the boundary, gaining energy from the electric fields present there. These processes at the cometopause can generate electromagnetic emissions across a wide range of frequencies. Some emissions are at such low frequencies that they're below the range of human hearing if converted to sound. Others are at higher frequencies, potentially in the range that could interfere with radio communications. The power of these emissions depends on the comet's activity level and the solar wind conditions, but for an active comet like Atlas, they could be significant enough to be detected at considerable distances. The question of whether these emissions from Atlas could have reached Earth and affected satellites depends on many factors. Electromagnetic waves propagate differently at different frequencies. Low-frequency waves can be guided by magnetic field lines, potentially following paths that bring them to Earth even if the comet is not directly connected to Earth by field lines. Higher frequency waves tend to propagate more directly, but are also absorbed more readily by the plasma in space. The solar wind itself can act as a transmission medium for disturbances from the comet. Waves and instabilities generated at the comet can propagate through the solar wind plasma, potentially reaching Earth days or weeks after they were generated. These disturbances might be modified as they propagate, changing frequency or amplitude, but retaining some signature of their cometary origin. Detecting such signatures requires careful analysis of satellite data, looking for patterns that correlate with the comet's position and activity. As we delve deeper into the electromagnetic nature of Atlas's tail, we begin to appreciate the incredible complexity of what might seem, at first glance, to be a simple phenomenon. The tail is not just a passive stream of material flowing away from the comet, but an active electromagnetic system, generating waves, accelerating particles, and potentially influencing the space environment far from the comet itself. Whether this influence extended to Earth's satellites remains an open question, but the possibility itself expands our understanding of how different parts of the solar system are connected. The study of cometary tails has implications beyond just understanding comets themselves. These tails are natural laboratories for studying plasma physics under conditions that can't be replicated on Earth. The processes occurring in cometary tails are similar to those in other astrophysical contexts. Stellar winds, planetary magnetospheres, even the jets from black holes. By studying how Atlas's tail formed, evolved, and potentially influenced its environment, we gain insights that apply throughout the universe. The fragmentation of Atlas added another layer of complexity to its tail dynamics. As the nucleus broke apart, each fragment began producing its own contribution to the tail, but these contributions didn't simply add together linearly. The interaction between material from different fragments created turbulence and structure that wouldn't have existed with a single source. The electromagnetic fields generated by one fragment's activity could influence the plasma environment around other fragments, creating a complex feedback system. This fragmentation may have also changed the tail's electromagnetic emissions. Multiple sources can create interference patterns, regions where waves from different sources reinforce each other, and regions where they cancel out. If the fragments were rotating or tumbling, as seems likely given the violent nature of the breakup, they would have created time-varying emissions, potentially producing a complex spectrum of frequencies. These emissions, though weak, would carry information about the fragmentation process itself, encoded in their frequency and intensity patterns. The dust released during fragmentation would have had its own electromagnetic story. Freshly exposed surfaces might charge differently than weathered surfaces that had been exposed to solar radiation for longer. Different minerals charge at different rates and to different potentials. The size distribution of particles released during fragmentation was probably different from that during normal sublimation, potentially creating a different electromagnetic environment in the post-fragmentation tail. As we continue to explore the mysteries of Atlas's tail, we're reminded of how much we still have to learn about these cosmic visitors. Each comet is unique, with its own composition, structure, and history. Atlas, with its spectacular brightening, subsequent fragmentation, and potential electromagnetic effects, has added new chapters to our understanding of cometary science. The possibility that it influenced satellites at Earth, even if eventually disproven, has pushed us to think more carefully about the electromagnetic connections in our solar system. The tail of Atlas was not just a beautiful sight in telescopes, but a complex electromagnetic phenomenon that connected the ancient ice of the outer solar system with the modern technology orbiting Earth. In this tail, processes that began billions of years ago when the comet formed continue to unfold, creating a bridge across time as well as space. The molecules that sublimated from Atlas have been frozen since the dawn of the solar system, and their ionization and acceleration in the tail released energy that had been stored for eons. This is the poetry of cometary science. These dirty snowballs from the edge of the solar system are messengers from the past, carrying information about conditions when the planets were forming. But they're also active participants in the present, influencing the electromagnetic environment of the inner solar system in ways we're still discovering. The tail of Atlas, stretching millions of kilometers through space, was both a record of the past and an actor in the present, a whispering veil that may have touched our satellites with its electromagnetic breath. Moving deeper into our cosmic contemplation, we must now turn our attention to the magnificent symphony of our star, the Sun, whose constant outpouring of particles and energy creates the very environment through which comets like Atlas must travel. Picture yourself now floating above the Sun's surface, though at a safe distance, of course, watching the constant dance of plasma and magnetic fields that creates what we call space weather. The Sun is not the steady, unchanging orb it appears to be from Earth, but rather a dynamic, breathing entity, sending out waves of particles and radiation that fill the entire solar system with an invisible wind. This solar wind, discovered only in the age of space exploration, is one of the most fundamental features of our cosmic neighborhood. It begins in the Sun's corona, that ethereal outer atmosphere visible during total solar eclipses as a shimmering halo around the darkened disk. The corona is mysteriously hot, millions of degrees, far hotter than the Sun's visible surface below it. This extreme temperature gives particles in the corona so much energy that they can escape the Sun's enormous gravity, streaming outward in all directions at speeds of hundreds of kilometers per second. The solar wind is not uniform or steady, but varies constantly in speed, density, temperature, and magnetic field strength. From the Sun's equatorial regions, a slow wind emerges, traveling at about 400 kilometers per second. From coronal holes, regions where the Sun's magnetic field opens directly into space, a fast wind flows at speeds that can exceed 800 kilometers per second. These different streams rotate with the Sun, creating a spiral pattern throughout the solar system, like water from a rotating garden sprinkler. Embedded within the solar wind is the Sun's magnetic field, stretched and carried outward by the flowing plasma. This creates what scientists call the interplanetary magnetic field, a vast spiral of magnetism that extends from the Sun to the outer reaches of the solar system. The field lines are like invisible threads connecting different regions of space, along which disturbances can propagate. When a comet like Atlas enters this environment, it doesn't just encounter a simple flow of particles but a complex electromagnetic system with its own dynamics and variability. The interaction between the solar wind and a comet is one of the most beautiful examples of plasma physics in nature. As the solar wind approaches the comet, it first encounters the outer reaches of the comet's atmosphere, where the density of cometary gas is still very low. Here, solar wind particles begin to collide with cometary molecules, ionizing them and beginning the process of mass loading we discussed earlier. The solar wind starts to slow down, and its magnetic field begins to drape around the obstacle presented by the comet. As we move closer to the comet, the interaction becomes more dramatic. The solar wind continues to slow, and at some point it can no longer flow at supersonic speeds. This creates a bow shock, similar to the shock wave that forms in front of a supersonic aircraft. At the bow shock, the solar wind is heated, compressed, and deflected around the comet. The kinetic energy of the flowing plasma is converted into thermal energy and electromagnetic energy, creating a region of intense activity. Behind the bow shock, in what's called the cometosheath, the solar wind flow becomes turbulent. The neat spiral pattern of the interplanetary magnetic field is disrupted, twisted, and tangled. Waves and instabilities develop, creating a chaotic electromagnetic environment. This is where much of the acceleration of cometary ions occurs, as they're picked up by the turbulent fields and accelerated to match the solar wind's speed. The solar wind during Atlas's passage was in an interesting state. We were near solar minimum, the quiet phase of the Sun's 11-year activity cycle. During solar minimum, the Sun produces fewer flares and coronal mass ejections, those explosive events that can send billions of tons of plasma racing through the solar system. The solar wind becomes more organized, with a clearer distinction between fast and slow streams. This relative simplicity might have made it easier for any electromagnetic effects from Atlas to propagate through the inner solar system without being overwhelmed by solar storms. But even during solar minimum, the Sun is far from quiet. The rotation of the Sun, combined with the different speeds of solar wind from different regions, creates what are called corrotating interaction regions. These are places where fast solar wind catches up with slow solar wind, creating compression regions with enhanced magnetic field strength and particle density. These interaction regions rotate with the Sun, sweeping through the solar system like the arms of a spiral galaxy. When Atlas encountered one of these regions, its interaction with the solar wind would have intensified, potentially enhancing any electromagnetic effects. The Sun also produces a constant flux of ultraviolet and X-ray radiation, which plays a crucial role in cometary activity. This radiation is what breaks apart molecules in the comet's coma, creating the ions that form the ion tail. It also heats the comet's surface, driving sublimation, and charges dust particles through the photoelectric effect. The intensity of this radiation varies with the solar cycle and can change dramatically during solar flares. Even small variations in solar ultraviolet output can affect a comet's activity level and consequently its electromagnetic influence. During Atlas's approach to the Sun, there were several minor solar events that might have influenced the comet's behavior. Small flares, too weak to affect Earth directly, could still have increased the ionization rate in the comet's coma. Variations in the solar wind speed would have changed the dynamics of the comet's tail, potentially creating waves or disconnection events. Changes in the interplanetary magnetic field orientation could have altered how cometary ions were picked up and accelerated. The relationship between solar activity and cometary behavior is complex and not fully understood. Some comets show increased activity when they encounter solar wind disturbances, perhaps because the increased pressure triggers additional sublimation, or because the enhanced electromagnetic environment affects how material escapes from the nucleus. Other comets seem relatively unaffected by solar variations, their activity dominated by their distance from the Sun rather than the details of the solar wind conditions. Atlas appeared to show some correlation between its brightness variations and solar wind conditions, though the relationship was complicated by its ongoing fragmentation. There were times when increases in the solar wind pressure seemed to coincide with brightening events, as if the comet was responding to the Sun's breath. Other times, the comet's behavior seemed independent of solar conditions, driven by its own internal processes of fragmentation and sublimation. The solar wind also determines how far a comet's influence can extend. In a slower solar wind, disturbances from the comet have more time to grow and develop before being swept away. In a faster wind, cometary effects are more quickly diluted and dispersed. The magnetic field strength in the solar wind affects how efficiently waves can propagate and how strongly charged particles are confined. During Atlas's passage, the solar wind conditions may have been particularly favourable for allowing cometary influences to reach Earth. One aspect of the solar wind that's particularly relevant to our satellite mystery is its role in determining Earth's magnetospheric conditions. The solar wind constantly buffets Earth's magnetic field, compressing it on the sunward side and stretching it into a long tail on the night side. Variations in the solar wind cause the magnetosphere to expand and contract, creating the geomagnetic storms that can affect satellites. If Atlas somehow modified the solar wind that subsequently encountered Earth, it could have indirectly influenced our satellites through changes in magnetospheric dynamics. The possibility of such an indirect influence is intriguing. Imagine Atlas as a stone thrown into the river of the solar wind. The ripples from that stone, in the form of waves, turbulence, or modified plasma properties, could propagate downstream and eventually wash over Earth. These ripples might be too weak to detect directly, but satellites, with their sensitive instruments and vulnerable electronics, might feel their effects. The anomalies recorded by satellites during Atlas's passage might not be from the comet itself, but from the solar wind's memory of its encounter with the comet. The solar wind also plays a role in the transport of cometary material through the solar system. Ions from the comet, once accelerated to solar wind speeds, become part of the solar wind itself, travelling outward through the solar system. Charged dust particles are influenced by the solar wind's electromagnetic fields. Their trajectory is altered from simple gravitational paths. Even neutral atoms from the comet can be ionized by solar radiation or charge exchange with solar wind ions, subsequently joining the flow. This means that cometary material doesn't just stay near the comet but can be distributed throughout the inner solar system. Spacecraft have detected cometary ions millions of kilometers from their source comets, identified by their composition and energy characteristics. If Atlas was producing significant amounts of ions and charged dust, this material could have been carried by the solar wind to Earth's vicinity, potentially interacting with our satellites even though the comet itself remained at a great distance. The Sun's magnetic field, carried by the solar wind, provides the framework for many of these interactions. Magnetic field lines can be thought of as highways for charged particles and waves. Disturbances at one point along a field line can propagate to other points, potentially connecting regions that are physically far apart. If magnetic field lines from the Sun happen to connect both Atlas and Earth at the same time, they could have provided a direct electromagnetic connection between the comet and our satellites. The complexity of the Sun's magnetic field in the inner solar system makes such connections possible but difficult to predict. The field is constantly being twisted by the Sun's rotation and distorted by the varying solar wind speed. Large-scale structures like the heliospheric current sheet, where the Sun's magnetic field changes polarity, sweep through the solar system. Smaller-scale structures like flux tubes and magnetic clouds add additional complexity. Atlas would have encountered all of these structures during its journey through the inner solar system, each encounter potentially affecting its electromagnetic behavior. Solar energetic particles present another aspect of the Sun's influence on cometary interactions. These are particles accelerated to high energies by solar flares or by shocks in the solar wind. When these particles encounter a comet, they can penetrate deep into the coma, causing ionization and possibly affecting the comet's chemistry. They can also create secondary particles through nuclear interactions, adding to the radiation environment around the comet. During Atlas's passage, there were several minor solar energetic particle events that might have influenced the comet's behavior. The Sun's influence extends even to the fragmentation of Atlas. While the primary cause of fragmentation was likely thermal stress from solar heating, the solar wind may have played a role too. The pressure from the solar wind, though tiny, acts differently on different parts of an irregular fragmenting nucleus. The electromagnetic forces from the interaction between the solar wind and the comet's plasma environment could have added additional stresses. The fragmentation might have been triggered or accelerated by encounters with solar wind structures like corrotating interaction regions. As we contemplate the Sun's role in the Atlas story, we're reminded of the interconnected nature of our solar system. The Sun is not just a distant source of light and heat, but an active participant in every cosmic drama that unfolds within its domain. Its wind, its magnetic field, its radiation all create the stage on which comets perform their spectacular shows. And sometimes, as may have been the case with Atlas, the Sun's influence can amplify or transmit a comet's effects to unexpected places like the satellites orbiting Earth. The dance between the Sun and Atlas was a complex choreography of electromagnetic forces, particle interactions, and energy exchanges. The Sun provided the energy that activated the comet, turning a frozen relic into a dynamic phenomenon. It provided the solar wind that shaped the comet's tails and potentially carried its influence throughout the inner solar system, and it provided the varying conditions that made each day of the comet's journey unique, creating a rich data set for scientists to analyze in their search for understanding. This solar cometary interaction is not unique to Atlas, but occurs with every comet that ventures into the inner solar system. Each encounter is an experiment in plasma physics, a test of our understanding of electromagnetic processes in space. Some comets, like Halley and Giotto, have been visited by spacecraft that directly measured the interaction. Others, like Atlas, we observe from afar, inferring the physics from remote observations. Each comet adds to our knowledge, revealing new aspects of how the Sun's influence shapes the behavior of these ancient visitors. The timing of Atlas's visit during solar minimum may have been fortuitous for scientific study. With the Sun in a relatively quiet state, any effects from the comet would stand out more clearly against the background of solar variability. The more organized solar wind of solar minimum might have allowed cometary disturbances to propagate more coherently, and the reduced interference from solar storms meant that satellites could potentially detect weaker signals that would otherwise be overwhelmed. As we drift deeper into this cosmic meditation, consider how the Sun's influence permeates every aspect of the Atlas story, from the first warming that began the comet's activation to the solar wind that shaped its tails. From the radiation that ionized its gases to the magnetic fields that guided its charged particles, the Sun was the conductor of this celestial symphony. And perhaps, through mechanisms we're still trying to understand, the Sun helped transmit Atlas's whispers to our satellites, creating a connection across millions of kilometers of seemingly empty space. The Sun reminds us that space is never truly empty, but filled with its breath, its light, its magnetic influence. Every object in the solar system, from the largest planet to the smallest dust grain, exists within this solar atmosphere. Comets like Atlas are not isolated actors, but participants in a solar system-wide electromagnetic ecosystem. Their behavior cannot be understood in isolation, but only in the context of their interaction with the Sun's pervasive influence. This brings us to consider the data itself, those faint electronic whispers recorded in the vast archives of satellite telemetry, waiting to tell their story to those patient enough to listen. In the quiet halls of data centers around the world, Servers hum with the accumulated observations of decades of satellite operations. Every measurement, every anomaly, every routine observation is stored, creating a detailed record of the electromagnetic environment around Earth. And somewhere in these archives, perhaps, lies evidence of Atlas's distant touch. The search for cometary influences in satellite data is like looking for a specific whisper in a crowded room. The normal operations of satellites generate vast amounts of data, telemetry on system health, scientific observations, communication traffic, navigation signals. Most of this data is routine, showing the expected variations from day to night, from season to season, from solar maximum to solar minimum. But occasionally there are anomalies, unexpected variations that don't fit the normal patterns. These anomalies can have many causes. A cosmic ray might flip a bit in a computer's memory. A piece of space debris might create a small electrical discharge as it impacts the satellite. Solar activity might create unexpected charges on the satellite's surface. Temperature variations might cause components to behave slightly differently. Distinguishing a potential cometary influence from all these other sources of variation requires careful detective work, looking for patterns that correlate with the comet's position and activity. The process begins with identifying the time period of interest. Atlas was discovered in December 2019 and remained visible until its complete disintegration in May 2020. But its potential electromagnetic influence might have extended beyond its visible lifetime. Ions and charged dust from the comet could have continued traveling through the inner solar system for weeks or months after the comet itself had faded. The search window thus extends from early 2020 through perhaps the middle of the year. Within this time window, researchers must examine data from multiple satellites to look for correlated anomalies. A single satellite reporting an unusual event might just be experiencing a random malfunction. But if multiple satellites report similar anomalies at similar times, it suggests an external cause. The pattern of which satellites are affected and when can provide clues about the nature and source of the disturbance. The types of data that might show cometary influences are diverse. Magnetometer readings might show unusual waves or variations in the magnetic field. Particle detectors might record fluxes of ions with unusual compositions or energies. Radio receivers might detect increased noise or interference. Optical sensors might see unexpected background light. Power systems might show variations in solar panel output or battery charging. Attitude control systems might work harder to maintain orientation. Each type of data provides a different window into the electromagnetic environment around the satellite. The challenge is that the expected effects are subtle, perhaps barely above the noise level of the instruments. Detecting them requires sophisticated statistical analysis, looking for weak correlations that might be missed by casual inspection. Scientists use techniques like superposed epoch analysis, where data from multiple events are aligned and averaged to reveal patterns that are invisible in individual cases. They use spectral analysis to look for characteristic frequencies that might indicate wave activity. They use machine learning algorithms to identify unusual patterns that human analysts might miss. The data from GPS satellites has been particularly interesting in the search for Atlas influences. These satellites maintain incredibly precise time standards, and any variation in signal propagation can be detected. During the period of Atlas's closest approach, several GPS satellites reported timing anomalies that required correction. The anomalies were small, nanoseconds to microseconds, but they were detected by the monitoring systems that constantly check the constellation's accuracy. What makes these timing anomalies intriguing is their pattern. They didn't affect all satellites equally, but seem to depend on the satellite's position relative to the Sun-Earth-Comet geometry. Satellites on the sunward side of Earth showed different effects than those in Earth's shadow. The anomalies also showed a temporal pattern, with peaks that seemed to correlate with changes in Atlas's brightness, suggesting a connection to the comet's activity level. Communication satellites provided another dataset rich with potential clues. These satellites constantly monitor the quality of the signals they relay, tracking parameters like signal-to-noise ratio, bit error rate, and power levels. During the Atlas passage period, several operators reported degraded signal quality that couldn't be explained by weather or known interference sources. The degradation was frequency-dependent, affecting some communication channels more than others, suggesting a dispersive medium like plasma was involved. The pattern of communication disruptions was particularly interesting when mapped geographically. Satellites serving certain regions seemed more affected than others, and the affected regions changed over time in a way that seemed to correlate with Earth's rotation and the comet's position. It was as if there was a beam or stream of influence sweeping across Earth's satellite constellation, affecting different satellites at different times. Earth observation satellites, with their sensitive instruments designed to measure subtle changes in Earth's environment, inadvertently became detectors for potential cometary influences. Several satellites reported calibration anomalies during the Atlas period. Instruments that should have seen consistent readings from stable calibration targets instead showed small variations. These variations were typically within the error margins of the instruments, but their correlation across multiple satellites suggested they might be real rather than random. The infrared sensors on some Earth observation satellites detected what appeared to be a very faint, diffuse emission that didn't match any known terrestrial or atmospheric source. The emission was barely above the detection threshold and might have been dismissed as instrument noise, except that similar signals were detected by multiple satellites. The spectral characteristics of the emission were consistent with fluorescence from cometary molecules, raising the possibility that Earth was passing through an extremely diffuse cloud of cometary material. Weather satellites in geostationary orbit provided a unique perspective on the potential Atlas influence. These satellites maintained fixed positions relative to Earth's surface, making them ideal for detecting changes in the space environment. Several geostationary satellites reported unusual variations in their local plasma environment during the Atlas period. Ion detectors showed changes in the flux and energy distribution of charged particles. Magnetometers detected waves and oscillations that didn't match the usual patterns of geomagnetic activity. The data from these geostationary satellites was particularly valuable because of their continuous coverage. Unlike satellites in lower orbits that constantly change position, geostationary satellites provide a steady stream of observations from a fixed location. This made it easier to identify unusual events and track their evolution over time. The data showed several instances of what appeared to be wave packets propagating through the magnetosphere, with characteristics that didn't match typical solar wind disturbances. Military satellites, though their data is often classified, have reportedly also detected anomalies during the Atlas period. Without access to the detailed data, we can only speculate about what these satellites might have observed, but their sophisticated sensors, designed to detect missile launches, nuclear explosions and other threats, are also excellent detectors of space weather phenomena. Any unusual electromagnetic activity in Earth's vicinity would likely have been recorded by these vigilant sentinels. The International Space Station, though not a satellite in the traditional sense, provided another source of data. The station's instruments recorded several unusual events during the Atlas period, including unexpected auroral displays at latitudes where they shouldn't occur, variations in the radiation environment, and anomalies in some scientific experiments. The astronauts aboard reported seeing unusual optical phenomena, though these subjective observations are difficult to quantify scientifically. One of the most intriguing data sets comes from the amateur radio community. Ham radio operators around the world constantly monitor the propagation conditions for radio waves, noting when distant stations can be heard and when normal communications are disrupted. During the Atlas period, there were numerous reports of unusual propagation conditions, with signals travelling farther than expected or being blocked when they should have gotten through. While these observations are anecdotal, the pattern of reports suggests something unusual was happening in Earth's ionosphere. The challenge in analysing all this data is distinguishing correlation from causation. Just because anomalies occurred during Atlas's passage doesn't mean the comet caused them. The Sun is constantly varying, Earth's magnetosphere is dynamic, and satellites themselves can develop problems independently. To establish a causal connection, scientists need to show not just that anomalies occurred, but that they occurred in a pattern consistent with cometary influence and inconsistent with other explanations. This is where computer modelling becomes crucial. Scientists can simulate the interaction between Atlas and the solar wind, predicting what kinds of disturbances might be generated and how they might propagate to Earth. They can model how cometary ions might be transported through the inner solar system, and what would happen when they encounter Earth's magnetosphere. They can calculate the expected electromagnetic emissions from the comet and determine whether they could be detected at Earth. These models provide testable predictions that can be compared with the observed data. The model suggests that several mechanisms could potentially allow Atlas to influence satellites at Earth. Waves generated by the comet's interaction with the solar wind could propagate along magnetic field lines, eventually reaching Earth's magnetosphere. Cometary ions, accelerated by the solar wind, could be transported to Earth and affect the local plasma environment. Dust from the comet, if it reached Earth's vicinity, could create a diffuse cloud that affects electromagnetic propagation. Electromagnetic emissions from the comet, though weak, might be detectable by sensitive satellite instruments. But the models also show that these effects would be extremely subtle, at the edge of detectability. The vast distance between Atlas and Earth means that any influence would be diluted by spreading and absorption. The dynamic nature of the solar wind means that any cometary disturbance would be modified, and possibly obscured by the time it reached Earth. The complexity of Earth's magnetosphere means that even if cometary influences reached Earth, their effect on satellites would depend on many factors. As researchers continue to analyse the data, new patterns and correlations are emerging. Some anomalies that were initially attributed to Atlas have been explained by other causes, but other anomalies remain unexplained, tantalizing hints that something unusual happened during the comet's passage. The investigation is ongoing, with new analytical techniques being developed and additional data being examined. The search for Atlas's influence in satellite data is more than just an academic exercise. It has practical implications for satellite operations and space weather prediction. If comets can indeed affect satellites at great distances, this needs to be considered in satellite design and operation. Space weather forecasts might need to include cometary influences, especially for large or particularly active comets. Our understanding of the electromagnetic environment of the inner solar system would need to be revised to include these subtle cometary effects. The data also has implications for our understanding of comets themselves. If Atlas could influence satellites at Earth, it suggests that comets are more electromagnetically active than previously thought. It might mean that the zone of cometary influence extends much farther than the visible tail. It could indicate that fragmentation events like Atlas create particularly strong electromagnetic disturbances. Each piece of evidence adds to our picture of comets as dynamic electromagnetic phenomena rather than simple dirty snowballs. As we contemplate these vast archives of data, these electronic memories of events in space, we're reminded of how much information our civilization now collects about its cosmic environment. Every satellite is a sentinel, every instrument a witness to the subtle dramas playing out in the space around Earth. The possible detection of Atlas's influence in this data would be a testament to both the sensitivity of our instruments and the interconnected nature of our solar system. The data tells us that space is not the empty void it might appear, but a realm full of activity, where influences can travel vast distances and where seemingly isolated events can have far-reaching effects. The whispers in the data from Atlas's passage, whether ultimately confirmed or refuted, have already taught us to look more carefully at the electromagnetic environment around Earth, to consider connections we might have overlooked, to appreciate the subtle ways different parts of our solar system interact. The story of Atlas took its most dramatic turn as the comet approached the Sun, when this ancient voyager began to come apart at the seams, dissolving back into the cosmic dust from which it had formed billions of years ago. As you settle deeper into peaceful contemplation, imagine watching this celestial dissolution not as a violent destruction, but as a gentle letting go, a return to origins, like watching a sandcastle slowly claimed by the tide, grain by grain returning to the beach from which it came. This great disintegration of Atlas was not an ending, but a transformation, and perhaps, in ways we're still trying to understand, it may have amplified the comet's ability to whisper across the vast distances of space. The fragmentation of comets is not unusual, though we rarely get to witness it in such detail as we did with Atlas. These ancient structures, held together by the weakest of forces in the cold of deep space, often cannot withstand the stresses of approaching the Sun. Think of Atlas as a snowball that had been kept in a freezer for billions of years, suddenly exposed to warmth, but not just any warmth. The intense radiation of our star, accompanied by the subtle but persistent forces of gravity pulling differently on different parts of its irregular body. The nucleus of Atlas, perhaps 2 kilometers across at the start of its journey, was really a collection of smaller pieces that had been frozen together in the distant Oort cloud, waiting through the eons for this moment of dissolution. The first signs that Atlas was in trouble came in early April 2020, when astronomers noticed that the comet's brightness, which had been increasing dramatically as it approached the Sun, suddenly began to fluctuate erratically. Where once there had been a steady brightening that had astronomers excited about the possibility of a spectacular naked-eye comet, there were now unpredictable variations, the light curve jumping up and down like a failing heartbeat. Images from large telescopes showed that the previously compact nucleus appeared elongated, stretched out along the direction of the comet's motion, as if it were being pulled apart by invisible hands. What was happening inside Atlas during those crucial days? We can only imagine, based on our understanding of cometary physics and computer simulations, the drama unfolding within that ancient chunk of ice and rock. The sun-facing side of the nucleus was heating dramatically, perhaps reaching temperatures where not just the volatile ices, but even water ice was sublimating rapidly. This created jets of gas erupting from the surface with enough force to actually push against the comet's weak gravity. Meanwhile, the night side remained cold, creating thermal stresses as different parts of the nucleus expanded and contracted at different rates. These thermal stresses were likely concentrated along pre-existing weaknesses in the nucleus, boundaries between the constituent chunks that had come together billions of years ago to form the comet. Think of it like the seams in a piece of clothing, the places where different pieces of fabric are joined together. Under stress, it's often these seams that fail first. In Atlas, these ancient seams, which had held firm through billions of years in the deep freeze of the Oort cloud, began to crack under the thermal and mechanical stresses of the comet's solar approach. The rotation of the nucleus added another layer of complexity to the fragmentation process. Comets often rotate in complex, non-principal axis modes, tumbling chaotically rather than spinning smoothly like a top. This tumbling creates time-varying stresses throughout the nucleus, as different parts experience different centrifugal forces. For a weakly bound structure like Atlas, these rotational stresses, combined with the thermal stresses from solar heating and the pressure from sublimating gases, created a perfect storm of forces working to tear the comet apart. The fragmentation appears to have begun with the nucleus splitting into several large pieces, each perhaps hundreds of meters across. These weren't explosive separations, but gentle driftings apart, the pieces moving away from each other at speeds of maybe meters per hour, barely a walking pace. But in the weak gravity of the comet, this was enough to overcome the feeble forces holding them together. Each piece retained the comet's orbital motion, continuing on essentially the same path around the Sun, but slowly spreading out along the orbit like pearls from a broken necklace drifting apart. Each fragment became, in essence, its own small comet, with its own coma of sublimating gases and its own contribution to the overall tail. But these fragments were themselves unstable, subject to the same stresses that had broken apart the original nucleus. Over the following weeks, the large fragments broke into smaller pieces, and those pieces fragmented further, creating a cascade of disintegration that ultimately reduced Atlas to a cloud of debris, ranging from boulder-sized chunks down to microscopic dust particles. This hierarchical fragmentation, where large pieces break into smaller pieces which break into even smaller pieces, is a fascinating process from a physics perspective. It's similar to how a wine glass shatters, with cracks propagating and bifurcating to create an ever finer pattern of fragments. But unlike a shattering glass, which happens in milliseconds, Atlas's fragmentation played out over weeks, slow enough for astronomers to watch and document each stage of the process. The fragmentation fundamentally changed how Atlas interacted with its environment. Instead of a single source of gas and dust, there were now dozens, perhaps hundreds of sources, each contributing to the comet's activity. The total surface area exposed to sunlight increased dramatically with each fragmentation event. Where once there had been perhaps 10 square kilometers of surface, there were now hundreds of square kilometers across all the fragments. This meant more sites for sublimation, more sources of gas and dust, potentially more electromagnetic activity. From an electromagnetic perspective, the fragmentation created a much more complex and interesting environment. Each fragment, as it sublimated and released charged particles, created its own small magnetosphere, its own region of electromagnetic influence. These mini-magnetospheres interacted with each other and with the solar wind in complex ways. Magnetic reconnection events, where magnetic field lines break and reconnect in new configurations, could have occurred between fragments, accelerating particles and generating waves. The cloud of fragments also created a broader interaction region with the solar wind. Instead of the solar wind encountering a single obstacle, it now had to flow around and through a dispersed cloud of obstacles. This created a more turbulent wake, a larger and more complex region of disturbed plasma downstream from the comet. If this disturbed region was carried by the solar wind toward Earth, it could have created a longer duration influence on our magnetosphere and satellites. The fragmentation also released different types of material than normal cometary activity. When a comet nucleus breaks apart, it exposes fresh surfaces that haven't been processed by solar radiation. These fresh surfaces might have different compositions, different volatile contents, different grain sizes. Material from the interior of the nucleus, protected from cosmic ray bombardment and solar heating for billions of years, was suddenly exposed. This pristine material might have sublimated more vigorously, creating bursts of activity as each new surface was exposed. The dust released during fragmentation was particularly interesting. Normal cometary activity tends to lift the smallest, lightest particles from the surface, but fragmentation can release a much broader range of particle sizes, including larger grains and even pebbles that wouldn't normally escape the nucleus. These larger particles, once released, follow different trajectories than the fine dust. They're less affected by radiation pressure, staying closer to the comet's orbital path. They also charge differently, potentially creating a more complex electromagnetic environment in the comet's vicinity. The spectroscopic observations of Atlas during its fragmentation revealed chemical variations between different fragments, suggesting that the original nucleus was heterogeneous, made up of regions with different compositions. Some fragments appeared richer in carbon compounds, others in water ice. This heterogeneity might reflect the different sources of material that came together to form the original nucleus billions of years ago, each preserving its own chemical signature from different regions of the early solar system. The fragmentation of Atlas created what astronomers call a debris trail, an extended cloud of material spread out along the comet's orbit. Unlike the tail, which points away from the sun, the debris trail follows the comet's path, marking where it has been. This trail consists of particles of all sizes, from dust to boulders, each following its own slightly different orbit depending on its size and the forces acting on it. Over time, this trail spreads out, eventually forming a stream of material that Earth might encounter in future years as a meteor shower. From the perspective of our satellite mystery, the debris trail is particularly intriguing. If Earth's orbit brought us through or near this trail, our satellites would have been flying through a cloud of cometary material, albeit an extremely diffuse one. Even if the density was far too low to pose any mechanical threat to satellites, the electromagnetic effects could have been significant. Each particle in the trail, especially the smaller ones, would likely be electrically charged. A satellite passing through such a cloud would experience a constantly changing electromagnetic environment as charged particles streamed past. The fragmentation also affected how Atlas's influence propagated through the solar system. Instead of a point source of disturbance, there was now an extended source region. Waves and instabilities generated by one fragment could interact with those from other fragments, creating interference patterns. The broader source region meant that any given point in space might be influenced by multiple fragments at different times, creating a more complex temporal pattern of disturbance. Computer simulations of the fragmentation process have revealed fascinating details about how the comet came apart. The models suggest that the fragmentation was not random, but followed patterns determined by the pre-existing structure of the nucleus. Fractures propagated along boundaries between different ice compositions, areas where the material properties changed. The spinning of fragments after separation was determined by the asymmetry of the gas jets, which acted like tiny rockets pushing the pieces into rotation. These simulations also suggest that the fragmentation might have created conditions for enhanced electromagnetic activity. As fragments separated, the space between them could have acted like a natural particle accelerator. Charged particles trapped between fragments could have been accelerated by the electric fields created by differential charging. Magnetic field lines stretched between fragments could have snapped and reconnected, releasing energy and accelerating particles to high speeds. The optical appearance of Atlas during fragmentation was remarkable and provided clues about the physical processes occurring. The comet appeared to breathe, brightening and fading over periods of hours to days. Each brightening event likely corresponded to a fragmentation event exposing fresh ice, followed by fading as the most volatile materials were exhausted. The color of the comet also changed during fragmentation, sometimes appearing more green from carbon emissions, other times more blue from ion emissions, suggesting changes in the dominant physical processes. Amateur astronomers around the world documented Atlas's fragmentation in unprecedented detail, contributing valuable observations to the scientific record. Their images showed the comet's nucleus stretching, dividing, and dispersing over the course of weeks. Some observers reported seeing distinct fragments through their telescopes, while others noted changes in the comet's overall appearance from night to night. This citizen science contribution was invaluable, providing near-continuous coverage that professional observatories alone couldn't achieve. The fragmentation of Atlas was also observed by several spacecraft, providing unique perspectives not available from Earth. The Solar Orbiter spacecraft, launched just months before Atlas's fragmentation, captured images of the comet from a different angle than Earth-based observers, helping to create a three-dimensional picture of the fragmentation process. The SOHO spacecraft monitoring the Sun caught glimpses of Atlas as it passed through its field of view, showing the comet's final approach to the Sun and ultimate dissolution. These spacecraft observations revealed details invisible from Earth, including the comet's behavior in extreme ultraviolet and X-ray wavelengths. These high-energy observations showed hotspots in the coma where particularly energetic processes were occurring, possibly sites of magnetic reconnection or particle acceleration. They also showed the comet's interaction with the solar wind in real time, capturing waves and instabilities as they developed. The ultimate fate of Atlas's fragments was dissolution into ever smaller pieces, until nothing remained but a cloud of dust and gas, gradually dispersing into interplanetary space. The largest fragments survived longest, continuing to sublimate and fragment for weeks after the initial breakup. But eventually, even these succumbed to the sun's heat and their own internal stresses, breaking apart into pieces too small to hold together. By late May 2020, Atlas had essentially ceased to exist as a discrete object, transformed from a single ancient nucleus into billions of tiny particles spreading throughout the inner solar system. This complete dissolution meant that Atlas's material was distributed over an enormous volume of space. The gas molecules, once released, were ionized by solar radiation and swept up by the solar wind, joining the general flow of plasma through the solar system. The dust particles, depending on their size, either spiraled toward the sun under Poynting-Robertson drag, were blown out of the solar system by radiation pressure, or settled into orbits that might eventually intersect with Earth or other planets. The electromagnetic legacy of Atlas's fragmentation could persist long after the comet itself disappeared. The charged particles released during fragmentation would continue to interact with the solar wind and interplanetary magnetic field. Waves generated by the fragmentation event could propagate through the solar system, potentially triggering instabilities far from their source. The enhanced dust environment created by the fragmentation could affect the propagation of electromagnetic signals, creating a subtle but measurable effect on radio communications. For our satellites, the fragmentation of Atlas might have created a prolonged period of subtle influence rather than a single brief encounter. As the cloud of fragments spread out along the comet's orbit and the debris dispersed through the inner solar system, Earth and its satellites might have experienced multiple passages through regions of enhanced cometary material. Each passage might have been too weak to cause obvious effects, but the cumulative influence over weeks or months could have been significant. The fragmentation also provides a natural explanation for the varied and sometimes contradictory anomalies reported by different satellites. If Earth was passing through a heterogeneous cloud of cometary debris, different satellites at different locations would experience different conditions. A satellite passing through a region rich in charged dust might experience charging anomalies, while another passing through a region of enhanced plasma might detect magnetic field disturbances. The temporal and spatial variation in the debris cloud could account for the complex pattern of satellite anomalies. As we reflect on the great disintegration of Atlas, we see it not as a destruction, but as a transformation, a return to the cosmic dust from which all things in our solar system ultimately came. The comet, which had preserved a sample of the early solar system for billions of years, released that sample back into space, enriching the interplanetary medium with ancient materials. Some of that material will eventually fall to Earth as microscopic meteorites, perhaps seeding our atmosphere with organic molecules. Some will spiral into the sun, returning to the stellar furnace, and some will continue to orbit, perhaps to be swept up by future comets, continuing the cosmic cycle of aggregation and dispersal. The fragmentation of Atlas reminds us of the impermanence of all structures in our universe, from the smallest dust grain to the largest galaxy. Everything is in constant change, constant transformation. Comets are particularly dramatic examples of this impermanence, these ancient objects that seem so permanent on human timescales, but are actually quite fragile and short-lived once they enter the inner solar system. Atlas existed as a single object for billions of years, but its time in the sun lasted only months before it returned to dust. This impermanence, however, doesn't diminish the comet's significance or its potential influence. Indeed, the fragmentation might have enhanced Atlas's ability to affect its environment, creating a broader zone of influence than an intact comet would have produced. The dissolution of Atlas into countless particles meant that its material, and potentially its electromagnetic influence, was spread over a much larger volume of space, increasing the chances that Earth and its satellites would encounter some portion of the comet's remains. As we continue our contemplation of cosmic connections, We turn now to the profound implications of what the Atlas event might mean for our understanding of the universe and our place within it. The possibility that a comet passing at such an enormous distance could influence our satellites challenges us to think differently about the nature of space and the connections between celestial objects. We live not in isolated bubbles, but in an interconnected cosmic web where influences can propagate across seemingly impossible distances, where the ancient past can reach out and touch our technological present. Consider the vast scales involved in this cosmic story. Atlas formed over 4.5 billion years ago before Earth existed, before life emerged, before any of the history we know unfolded. It spent those billions of years in the deep freeze of the Oort cloud, a region so distant that light from the sun takes perhaps a year to reach it. Then, disturbed by some cosmic nudge, it began its long fall toward the sun, a journey of thousands of years through the darkness. For all those millennia, it was approaching its appointment with our era, carrying its ancient cargo toward a meeting with our civilization's technology. When Atlas finally arrived in the inner solar system in 2020, it encountered a world transformed beyond all recognition from the one that existed when the comet formed. Where once there were only barren rocks orbiting young star, there was now a living planet, covered with life, surrounded by artificial satellites, home to a technological civilization capable of detecting and studying visitors from the edge of the solar system. The comet, in its dissolution, might have whispered to those satellites, creating a connection between the ancient and the modern, the natural and the artificial. This connection, if real, would represent something profound about the nature of our universe. It would mean that we're even more intimately connected to the cosmos than we realized. We already knew that we are made of star stuff, that the atoms in our bodies were forged in the nuclear furnaces of dying stars. We knew that Earth is constantly bombarded by cosmic rays, solar wind and meteorites, connecting us physically to the wider universe. But if Atlas could electromagnetically influence our satellites from millions of kilometers away, it suggests an even more subtle and pervasive web of connections. Think about what this means for our understanding of space. We tend to think of space as empty, a vacuum through which objects move in isolation, interacting only when they come close together. But the Atlas event suggests that space is more like an ocean, where every movement creates waves that propagate outward, potentially affecting distant shores. The electromagnetic fields that permeate space, the streams of charged particles, the waves and instabilities in the plasma, all create a medium through which influences can travel far beyond what we might expect. This has implications for how we think about our technological civilization. We've surrounded our planet with satellites, assuming they operate in a relatively predictable environment, affected mainly by Earth's magnetosphere and direct solar activity. But if comets can influence satellites, what other cosmic phenomena might have subtle effects on our technology? Could supernovae in distant galaxies create electromagnetic pulses that affect our electronics? Could the passage of interstellar clouds change the propagation of radio signals? Could the alignment of planets create electromagnetic resonances that influence satellite operations? These questions might seem far-fetched, but the history of science is full of discoveries of unexpected connections. Who would have thought that tree rings could tell us about ancient climate? That ice cores could reveal the composition of Earth's atmosphere hundreds of thousands of years ago? That the cosmic microwave background could tell us about the universe's first moments? Each of these discoveries revealed connections across vast scales of space and time, showing us that everything in the universe is more connected than we imagined. The Atlas event also raises philosophical questions about causation and influence. In our everyday experience, cause and effect are usually clear and direct. You push something and it moves. You heat something and it expands. But in the cosmic realm, causation can be subtle and indirect. A comet fragmenting millions of kilometers away might create electromagnetic waves that propagate through space, interact with the solar wind, modify Earth's magnetosphere, and ultimately cause a satellite to experience a tiny anomaly. The chain of causation is long and complex, with each link adding uncertainty, but the connection might still be real. This complexity reminds us of chaos theory and the butterfly effect, the idea that small changes can have large consequences in complex systems. Could the fragmentation of Atlas be like the butterfly's wings, creating tiny disturbances that propagate and amplify through the electromagnetic environment of the solar system? Could those ancient ices sublimating in the warmth of the sun have set in motion a cascade of effects that ultimately touched our most advanced technology? The possibility of cometary influence on satellites also has practical implications for space exploration and colonization. As we send more spacecraft farther into the solar system, they will encounter more comets, asteroids, and other small bodies. If these objects can have electromagnetic effects at great distances, we need to consider this in spacecraft design and mission planning. Future Mars colonies might need to monitor approaching comets, not just for potential impact, but for electromagnetic effects. Spacecraft traveling to the outer planets might need to account for the influence of the many comets that orbit in those regions. For Earth, the Atlas event suggests we need to expand our concept of space weather. Currently, space weather forecasting focuses mainly on solar activity, flares, coronal mass ejections, solar wind variations. But if comets can influence the near-Earth environment, they should be included in space weather models. Large comets approaching the inner solar system might need to be monitored, not just for their visual appearance, but for their potential electromagnetic effects. Satellite operators might need to be alerted when Earth is predicted to pass through a comet's debris trail or ion tail. The interconnectedness revealed by the Atlas event extends beyond just electromagnetic effects. Comets are carriers of water and organic molecules, the building blocks of life. Every comet that passes through the inner solar system deposits some of its material, enriching the planets with these crucial compounds. Earth receives tons of cometary material every day in the form of microscopic dust particles. Some scientists believe that comets delivered much of Earth's water, and perhaps even the organic molecules that led to life. If Atlas influenced our satellites, it means that this ancient carrier of prebiotic molecules came close enough to touch our technology with its electromagnetic fingers. The same object that might have carried ingredients for life was interacting with the products of that life billions of years later. There's a poetic circularity to this, a closing of a cosmic loop that began when the solar system formed and continues today as we reach out into space with our technology. The study of Atlas and its potential effects also highlights the importance of international cooperation in understanding our cosmic environment. The comet was discovered by a survey funded by NASA, observed by telescopes around the world, and its potential effects on satellites involve spacecraft operated by many nations. Understanding cosmic phenomena requires pooling resources, sharing data, and collaborating across borders. The universe doesn't respect national boundaries, and neither should our efforts to understand it. This global collaboration in studying Atlas is a small example of how cosmic events can unite humanity. When we face influences from beyond Earth, our terrestrial divisions seem less important. We're all on the same small planet, all subject to the same cosmic forces, all part of the same story. Perhaps this is one of the most important lessons from events like Atlas. They remind us of our shared vulnerability and our common heritage as children of the cosmos. The possibility that Atlas influenced satellites also underscores the importance of maintaining comprehensive records of both cosmic events and technological operations. The anomalies in satellite data might have gone unnoticed if we didn't keep detailed logs. The connection to Atlas might never have been suspected if we didn't track comets and their behavior. This highlights the value of what might seem like routine data collection and storage. Today's routine observation might be tomorrow's crucial clue to understanding some cosmic mystery. As we look to the future, the Atlas event suggests that we need to develop new instruments and techniques for detecting subtle cosmic influences. Perhaps we need satellites specifically designed to monitor the electromagnetic environment, with sensors capable of detecting the weak signals from distant comets. Perhaps we need networks of instruments that can triangulate the source of electromagnetic disturbances. Perhaps we need artificial intelligence systems that can sift through vast amounts of data to find subtle correlations that human analysts might miss. The Atlas event also reminds us to remain humble about our understanding of the universe. Despite all our scientific advances, we're still discovering new phenomena, new connections, new ways that different parts of the cosmos interact. Every comet that visits the inner solar system is an opportunity to learn something new, to test our theories, to expand our understanding. Atlas, in its brief appearance and dramatic fragmentation, taught us that even seemingly well-understood phenomena like comets can still surprise us. The legacy of Atlas will continue long after the comet itself has dispersed into cosmic dust. The particles released during its fragmentation will continue orbiting the Sun, some eventually falling to Earth as meteors, others joining the zodiacal cloud of dust that fills the inner solar system. The ions accelerated during the comet's interaction with the solar wind have joined the general population of particles flowing through space. The electromagnetic waves generated by the comet have propagated outward, becoming part of the background noise of the universe. And perhaps, in ways we're still trying to understand, Atlas left its mark on our satellites, those artificial sentinels that monitor our planet and connect our global civilization. If confirmed, this influence would add a new chapter to the story of Comet-Earth interactions, showing that these cosmic visitors affect us in more ways than we imagined. Even if the influence is ultimately disproven, the investigation itself has value, pushing us to think more carefully about the electromagnetic environment of space and the subtle connections between celestial objects. As we contemplate these vast scales and subtle connections, we're drawn to consider what other cosmic influences might be affecting us without our knowledge. How many comets have passed through the inner solar system during the satellite age, their potential electromagnetic effects unnoticed because no one thought to look for correlations? How many anomalies in satellite data have been dismissed as random noise when they might have been whispers from passing cosmic visitors? The Atlas event, whether its influence on satellites is real or not, has opened our eyes to possibilities we hadn't considered before. This expansion of awareness is perhaps the most important legacy of Atlas. It has reminded us to look for connections across vast scales, to consider influences that seem impossibly subtle, to remain open to surprises from the cosmos. It has shown us that our technological civilization, for all its sophistication, exists within and depends upon a cosmic environment that we're still learning to understand. Our satellites, those pinnacles of human engineering, float in an ocean of electromagnetic fields and particle streams that connect them to the entire solar system and beyond. The story of Atlas also illustrates the importance of serendipity in scientific discovery. No one expected this comet to potentially influence satellites. The comet was interesting for other reasons: its brightness, its fragmentation, its composition. The possible satellite effects were discovered only because some researchers thought to look for correlations, to ask, what if? This reminds us that some of the most important discoveries come not from planned experiments, but from unexpected observations, from following curious anomalies wherever they lead. As we move deeper into the space age, with plans for lunar bases, Mars colonies, and missions to the outer planets, understanding subtle cosmic influences becomes increasingly important. Future space travelers might need to worry not just about radiation and meteoroid impacts, but about electromagnetic effects from comets, asteroids, and other phenomena. The Atlas event, if confirmed, would be an early warning that space is more complex and interconnected than our current models suggest. The interconnectedness revealed by Atlas extends to time as well as space. The comet connected the deep past, when the solar system formed, to the present, when our satellites detected its possible influence. It reminds us that we exist not at a single moment but within a vast temporal context, influenced by events that happened billions of years ago and influencing events that will happen billions of years in the future. Our satellites, recording their data, are creating a record that future scientists will use to understand cosmic events we can't yet imagine. This temporal connection raises profound questions about our place in cosmic history. We happen to live at a time when we can detect and study comets, when we have satellites that might feel their influence, when we can begin to understand these subtle connections. Earlier civilizations could only watch comets with awe and fear, unable to understand their nature. Future civilizations might have even more sophisticated ways of detecting cosmic influences. We exist at a unique moment, with just enough technology to detect these effects, but still much to learn about their nature and implications. The Atlas event also highlights the role of imagination in scientific discovery. Someone had to imagine that a comet might influence satellites, had to think beyond the conventional understanding that such effects were impossible at such distances. This imaginative leap, backed by careful analysis and data, is what drives science forward. It reminds us that the universe is often stranger and more wonderful than we imagine, that connections exist where we don't expect them, that influences can propagate in ways we haven't considered. As we near the end of our contemplation of Atlas and its potential influence on satellites, we're left not with definitive answers, but with a sense of expanded possibility. The universe reveals itself to be more interconnected than we thought, with influences propagating across vast distances through subtle electromagnetic effects. Our satellites, those symbols of human technological achievement, are revealed to be not isolated machines but participants in a cosmic, electromagnetic ecosystem, potentially touched by ancient comets passing millions of kilometers away. The beauty of this uncertainty, this not knowing for sure whether Atlas influenced our satellites, is that it keeps the mystery alive, keeps us questioning and investigating. Science is not about having all the answers, but about asking better questions, about remaining open to surprise, about following the evidence wherever it leads. The Atlas event has given us new questions to ask, new connections to investigate, new possibilities to consider. And now, as we approach the end of our journey through this cosmic mystery, we find ourselves not at a destination, but at a new beginning. The question of whether Atlas interfered with satellites has led us through billions of years of cosmic history, from the formation of the solar system to the fragmentation of an ancient comet, from the electromagnetic complexity of space to the sensitive instruments of our satellites. We've explored connections across vast scales of space and time, considered influences that seem almost impossibly subtle, and glimpsed the interconnected nature of our universe. The beauty of unanswered questions is that they keep us searching, keep us wondering, keep us connected to the mystery and majesty of the cosmos. As you drift towards sleep tonight, perhaps you can hold this question gently in your mind, not as something that needs to be solved, but as something to be appreciated for its own sake. Did Atlas interfere with satellites? Perhaps. Perhaps not. But in asking the question, in following its implications and considering its possibilities, we've already gained something valuable, a deeper appreciation for the subtle connections that bind everything in our universe together. Think of all the questions that surround us, floating in the darkness like stars waiting to be noticed. Each question is a doorway to wonder, an invitation to explore, a reminder that the universe is far more mysterious and beautiful than we can imagine. The question of Atlas and the satellites is just one among countless mysteries, but it's one that has led us on a remarkable journey through space and time, through science and imagination, through the known and the unknown. Questions, you see, are more valuable than answers in many ways. Answers close doors, ending the search, finalizing our understanding. But questions open doors, inviting exploration, encouraging us to look more carefully, think more deeply, imagine more boldly. The question of whether Atlas influenced satellites has opened doors to understanding electromagnetic connections in space, the fragility and complexity of comets, the sensitivity of our technology to cosmic influences, and the interconnected nature of everything in our solar system. Consider how this single question has expanded our awareness. Before Atlas, few people thought about the possibility of comets influencing satellites at great distances. The conventional wisdom was that such effects were impossible, that the distances were too vast, the influences too weak. But by asking "what if?" and following the evidence, we've discovered that the impossible might be merely unlikely, that the universe might be more connected than we thought. This expansion of possibility is the gift that questions bring. The reason why I don't know can be more exciting than I know. The question of Atlas also reminds us that the universe doesn't owe us answers. It exists in its vast complexity whether we understand it or not. Comets have been fragmenting and creating electromagnetic disturbances for billions of years, long before humans existed to observe them. Satellites experience anomalies whether we can explain them or not. The cosmos unfolds according to its own laws and patterns, yet indifferent to our desire for understanding. This humility in the face of cosmic mystery is perhaps one of the most important lessons from the Atlas event. Yet even without definitive answers, the question has been productive. It has led to new research, new collaborations between scientists, new ways of analyzing satellite data. It has prompted engineers to think about potential cosmic influences on spacecraft design. It has inspired amateur astronomers to observe comets more carefully, looking for signs of fragmentation and unusual activity. It has added to our catalogue of cosmic phenomena that might affect our technology. The question itself, regardless of its ultimate answer, has advanced our understanding. This is how science progresses, not in a straight line from ignorance to knowledge, but in a spiral of questions and partial answers, each answer generating new questions, each question revealing new depths of complexity. The Atlas question is part of this spiral, building on previous questions about comets and satellites, and leading to new questions about electromagnetic connections in space. Future scientists will build on what we've learned from Atlas, asking questions we can't yet imagine, discovering connections we can't yet conceive. The question also connects us to the grand tradition of astronomy, humanity's oldest science. For thousands of years, humans have looked at comets and wondered what they are, what they mean, how they affect us. Ancient astronomers recorded comet appearances, trying to correlate them with earthly events. Medieval scholars debated whether comets were atmospheric or celestial phenomena. Enlightenment scientists calculated cometary orbits and predicted their returns. Modern astronomers send spacecraft to visit comets and analyze their composition. The question of Atlas and satellites is the latest chapter in this long conversation between humanity and the cosmos. In a sense, every question about the universe is a question about ourselves. When we ask whether Atlas influenced satellites, we're really asking about our place in the cosmic order. Are we isolated on our planet, protected from cosmic influences by distance and Earth's magnetosphere? Or are we intimately connected to everything in the solar system, affected by distant comets in ways we're only beginning to understand? The answer shapes not just our scientific understanding, but our philosophical and spiritual relationship with the universe. The beauty of the Atlas question is that it exists at the intersection of the ancient and the modern, the natural and the technological. Comets are among the oldest objects in the solar system, preserving materials from the solar system's birth. Satellites are among our newest creations, products of the space age that began just decades ago. The possibility that one influenced the other creates a bridge across billions of years, a connection between the primordial and the contemporary. This temporal bridge reminds us that we exist not in a single moment, but in a continuous flow of cosmic history. The atoms in our bodies, in our satellites, in everything around us, have existed since the early universe. They've been part of stars, planets, comets, and countless other structures. The question of Atlas and satellites is just one brief chapter in the much longer story of these atoms, their interactions and transformations. We're privileged to be conscious witnesses to this tiny portion of cosmic history, able to ask questions about connections and influences that span vast scales of space and time. As you lie there in the darkness, perhaps you can feel yourself as part of this cosmic story, not separate from it, but woven into it. The same electromagnetic forces that might have carried Atlas's influence to our satellites flow through your body, maintaining the chemical bonds that hold you together. The same atoms that sublimated from Atlas exist in you, recycled countless times through cosmic history. You're not observing the universe from outside, but from within, as an integral part of the system you're trying to understand. This participatory universe, where observer and observed are part of the same system, adds another layer of beauty to unanswered questions. When we ask whether Atlas influenced satellites, we're not neutral observers but participants in the phenomenon. Our satellites are part of the electromagnetic environment of near-Earth space. Our observations of Atlas influenced how we understood and responded to the comet. Our questions shape what we look for and therefore what we find. The question itself becomes part of the cosmic story it's trying to understand. The uncertainty surrounding Atlas's influence on satellites also reminds us of the importance of mystery in human experience. We live in an age that often demands immediate answers, definitive explanations, complete understanding. But mystery is valuable in its own right. It keeps us humble, curious, open to possibility. It reminds us that the universe is larger and more complex than our theories. It invites us to remain in a state of wonder, rather than rushing to premature conclusions. Think of how different our experience of Atlas would be if we had immediate definitive answers to all our questions. If we knew exactly whether and how it influenced satellites, the mystery would be solved, the case closed. But because we don't know for certain, Atlas remains alive in our imagination, a source of ongoing wonder and investigation. The question mark after "Did Atlas interfere with satellites?" is not a failure of science, but an invitation to continued exploration. This ongoing exploration is what makes science a living, breathing endeavor rather than a static collection of facts. Every unanswered question is a job opening for future scientists, an invitation for someone to make a discovery, to add to human understanding. Perhaps someone reading about Atlas today will be inspired to study cometary electromagnetism, to develop new instruments for detecting subtle cosmic influences, to solve mysteries we haven't even identified yet. The unanswered question is a seed that might grow into future knowledge. The Atlas question also illustrates the collaborative nature of cosmic investigation. No single person or institution could answer whether Atlas influenced satellites. It requires astronomers to observe the comet, engineers to understand satellite operations, plasma physicists to model electromagnetic interactions, data scientists to analyze vast archives of information. It requires international cooperation, sharing of data across institutions and borders. The question brings together diverse expertise, creating connections not just in space but among humans working toward understanding. As we float here in the darkness, contemplating cosmic mysteries, we can appreciate how questions like the Atlas puzzle enrich our lives. They remind us that we live in a universe full of wonders, where even seemingly simple phenomena like a comet passing by can reveal unexpected depth of complexity. They connect us to something larger than ourselves, to cosmic processes that dwarf our everyday concerns. They invite us to exercise our imagination, to think beyond the boundaries of current knowledge. The question of Atlas and satellites is also a reminder of the contingency of cosmic events. If Atlas had arrived a few years earlier or later, our satellite constellation would have been different. If it hadn't fragmented, its electromagnetic signature would have been different. If Earth had been at a different point in its orbit, we might have passed through different parts of the comet's tail. The actual event we observed was just one of countless possible variations, a single realization of cosmic possibility. This contingency extends to our ability to observe and understand cosmic events. We happen to live at a time when we have satellites that could potentially detect cometary influences. We have computers powerful enough to analyze the vast amounts of data involved. We have a scientific framework that allows us to ask such questions. Earlier or later in human history, the Atlas event would have passed unnoticed or been interpreted completely differently. We exist in a unique window of capability and understanding. Yet even with all our technology and knowledge, the universe keeps surprising us. Atlas was expected to be a fairly ordinary comet until it began brightening dramatically. Its fragmentation was unexpected. The possibility of satellite influence was unconsidered until someone thought to look for it. These surprises remind us that our models and theories are always provisional, always subject to revision when new observations don't fit our expectations. The universe is under no obligation to conform to our understanding of it. This constant potential for surprise is what keeps science vibrant and exciting. If we knew everything, if there were no more questions to ask, the universe would be a much less interesting place. But every answered question reveals new questions. Every solved mystery unveils new mysteries. The Atlas event, whether it influenced satellites or not, has revealed new questions about cometary electromagnetics, about the sensitivity of satellites to cosmic influences, about the interconnectedness of the solar system. As we drift toward the conclusion of our contemplation, we can appreciate how a single question has taken us on a journey through space and time, through certainty and uncertainty, through science and philosophy. The question, did Atlas interfere with satellites, has been our guide, leading us to explore the nature of comets, the complexity of space, the sensitivity of our technology, and the interconnectedness of everything in our cosmic neighborhood. But the journey doesn't end with an answer. Whether future research definitively proves or disproves Atlas's influence on satellites, new questions will arise. If the influence is confirmed, we'll need to understand the mechanisms, predict future events, protect our technology. If it's disproven, we'll need to explain the anomalies another way, understand what we misunderstood, refine our models. Either way, the investigation continues, the questions proliferate, the mystery deepens. This is the beauty of cosmic questions. They don't really end. Each question is part of an infinite regress of curiosity, stretching back to the first humans who looked at the night sky and wondered, and forward to future beings we can't imagine, asking questions we can't conceive. The question of Atlas and satellites is one note in this vast symphony of inquiry, one thread in the infinite tapestry of cosmic investigation. As you prepare to drift into sleep, perhaps you can rest in the beauty of not knowing, in the peace of unanswered questions. The universe doesn't demand that we understand everything. It invites us to explore, to wonder, to ask questions, but it doesn't require answers. Sometimes the question itself is enough. The act of wondering is its own reward. The state of not knowing is a form of openness to the infinite mystery of existence. The story of Atlas reminds us that we are part of something vast and beautiful, something that extends far beyond our small planet and brief lives. We are connected to ancient comets and distant stars, to the deep past and the far future. Our satellites circling overhead are part of this cosmic dance, potentially touched by influences from the edge of the solar system. We ourselves are cosmic beings, made of star stuff, shaped by cosmic forces, participants in a story billions of years in the making. And in this cosmic story, questions are more precious than answers, mysteries more valuable than certainties. The question of whether Atlas interfered with satellites is a gift, an invitation to wonder, a doorway to the infinite. Whether answered or not, it has already served its purpose. It has made us think, made us wonder, made us look more carefully at the universe around us. It has reminded us that we live in a cosmos full of surprises, where ancient ice can whisper to modern machines, where the past can touch the present across millions of kilometers of space. So let the question remain open, let the mystery persist, let the wonder continue. Did Atlas interfere with satellites? Perhaps we'll know someday. Perhaps we won't. But in the questioning, in the wondering, in the contemplation of possibility, we've already received the greatest gift the cosmos can offer, a glimpse of its infinite complexity and beauty, a reminder of our place in the grand scheme of things, an invitation to remain forever curious about the universe we inhabit. As sleep approaches, you can release the need for answers and rest in the beauty of questions. The universe will continue its dance whether we understand it or not. Comets will continue to visit the inner solar system. Satellites will continue their orbits. And occasionally, perhaps, the two will interact in ways that surprise and delight us. We are witnesses to this cosmic ballet, participants in this grand experiment, questioners in the face of infinite mystery. The night sky above you holds countless questions, each star a mystery, each point of light a story waiting to be discovered. Atlas has returned to the darkness from which it came, dissolved into cosmic dust, but its question remains, floating in the space between knowledge and mystery, between the known and the unknown, and there, in that space of uncertainty, in that realm of possibility, we find the true beauty of cosmic contemplation, not in having all the answers, but in being part of a universe wonderful enough to inspire such questions. Rest now in this cosmic uncertainty, this peaceful not knowing. Let the question of Atlas and satellites be a gentle reminder that the universe is larger than our understanding, more connected than we imagined, more mysterious than we can grasp. You are part of this mystery, connected to it all, from the ancient comets to the modern satellites, from the distant past to the far future. And in this connection, in this participation in cosmic wonder, you can find peace, drifting off to sleep surrounded by the infinite questions of the universe, held in the gentle embrace of cosmic mystery, forever part of the beautiful unknown that stretches from here to the edge of existence and beyond.